So, here's something worth thinking about as you settle in tonight. Right now, passing through the room you are lying in, there is light that has been traveling for 13.8 billion years. It is landing on the walls. It is landing on you. Roughly 400 photons of it in every cubic centimeter of the space around your bed, arriving from every direction at once. And it left its source before there was a single star anywhere in existence. That light is the oldest thing you will ever be touched by. And tonight, we are going to follow it all the way back, slowly, to the moment people started calling the Big Bang. If you drift off somewhere along the way, that's perfectly fine. None of this is going anywhere. Let's start where the story actually starts, which is not with an explosion at all. It starts with somebody noticing that the night sky is dark. That sounds like the least interesting observation anybody has ever made. Of course, the night sky is dark. The sun has gone down. But sit with it a moment longer than is comfortable, and it stops being obvious. It starts being one of the strangest facts available to anyone who has ever looked up. Here's the problem. For most of recorded history, educated people assumed the universe was infinite, unchanging, and filled more or less evenly with stars. That was the default picture. Not a wild theory, just the sensible assumption. Space goes on forever, stars are scattered through it, and it has always been that way. It seems harmless enough. But if that is true, then look in any direction you like. Any direction at all. Pick a random line out from your window and follow it. If space goes on forever, and stars are scattered evenly through it forever, then that line has to hit a star eventually. It might travel a very long way first, but there is no escaping it. Given infinite distance and infinite stars, every single line of sight terminates on a burning surface, which means the entire sky should be a solid sheet of light, not sprinkled with points. Solid. Every square inch of it should be about as bright as the surface of the sun, because every square inch of it would be looking directly at one. The night sky is not like that. The night sky is mostly black. So which part of the assumption is wrong? Does space stop somewhere? Are the stars not evenly spread? Or is there something nobody had thought of at all? And that gap between what the sensible assumption predicts and what your own eyes report is one of the oldest unresolved problems in the history of astronomy. Thomas Digges ran into it in 1576, when he became one of the first people in England to argue that the stars are not fixed to a shell, but extend outward without limit. He noticed the difficulty and waved it away by suggesting that the distant stars were simply too faint to see, which is a reasonable instinct, and it is wrong, and we will come back to why. Johannes Kepler saw it more clearly in 1610. He used it as an argument against an infinite universe. If the sky is dark, Kepler reasoned, the universe must be bounded. There must be a wall out there somewhere. He preferred a finite cosmos with a dark enclosure around it, and the darkness overhead was his evidence. Edmund Halley worried at it in 1721. Jean-Philippe de Chazot worked on it in 1744 and proposed that some invisible fluid out in space was absorbing the light on its way to us. Heinrich Olbers made essentially the same suggestion in 1823. For reasons that are mostly historical accident rather than fairness, his name is the one that stuck to it. You will find it in textbooks as Olbers' paradox, even though Olbers was neither the first to notice it nor the one who solved it. The absorbing fluid idea is elegant, and it fails immediately. And it fails for a beautiful reason. If there were dust or gas out there soaking up starlight for long enough, it would heat up. It would keep heating up. And eventually, it would reach the same temperature as the stars around it. Then it would glow just as brightly as the thing it was hiding. You cannot hide a fire behind a blanket forever. The blanket catches. So the paradox sat there, genuinely open, genuinely embarrassing, for something like 300 years. And the person who got closest to the answer first was not an astronomer. He was a writer, in bad health, more or less broke, with about a year left to live. In 1848, Edgar Allan Poe published a strange, sprawling piece of work called Eureka. He called it a prose poem. He also seems to have meant it entirely seriously, which is part of why nobody in the sciences took it seriously at all. It is 150 pages of cosmology written by a man best known for stories about premature burial. It is full of things that are simply wrong. It is also, in one specific passage, correct in a way that nobody else would manage for another 80 years. Poe's answer to the dark sky was this: the reason we do not see a star in every direction is that the light from the most distant ones has not arrived yet. The universe has not been around long enough. There has not been sufficient time for the far light to cross the gap. That is the answer. That is genuinely the answer, and it is worth understanding exactly why, because it is the first place in this story where time and space stop being separate things and start being one thing. Light does not travel instantly. It moves at a fixed speed, and that speed, while enormous, is finite, which means that looking out into space is identical to looking backward into time. There is no way to do one without the other. When you look at the moon, you see it as it was 1¼ seconds ago. The sun, 8 minutes and 20 seconds. The nearest star beyond the sun, a little over 4 years. Andromeda, the furthest thing you can see with your eyes alone on a dark night, 2.5 million years ago. You are not looking at Andromeda. You are looking at a 2.5 million-year-old photograph of Andromeda, and there is no other kind available. So now, go further. Keep going out, which means keep going back. Eventually you reach a distance where the light has been traveling for the entire age of the universe, and past that point, there is nothing to see. Not because nothing is there, but because whatever is there has not had time to reach you. The message is still in transit. There is a horizon, and it is made of time rather than distance. That is why your sky is dark. Not because space ends, because the universe has a finite age, and the light beyond a certain distance simply has not got here. Poe worked that out in a book almost nobody read. He died the following year in Baltimore under circumstances that have never been fully explained. His cosmology was ignored for over a century. It gets a respectful footnote now, which is more than it had. And the fact that the correct answer to the dark sky is the finite age of the universe should tell you something about the shape of the rest of this. The universe has an age. It has not simply always been. Something happened, or at least something started, and everything you can see carries the fingerprint of it. But nobody in 1848 was in any position to prove that. To get from there to here, 3 separate things had to happen. Somebody had to build a theory of gravity that could describe the universe as a whole. Somebody had to find a way to measure distances to things far outside our own galaxy. And somebody had to notice what those distant things were doing. Those 3 things happened between 1915 and 1929, roughly 14 years. They were done by people who mostly did not agree with each other, and in several cases did not believe their own results. Let's start with the theory. In November of 1915, in Berlin, in the middle of a war, Albert Einstein finished the field equations of general relativity. He had been working toward them for 8 years, and the final month was a scramble, with a rival mathematician named David Hilbert closing in on the same result from a different direction. Einstein got there. The equations are compact enough to write across the width of a page. What they say is easy to state and very difficult to hold in your head. Gravity is not a force. Nothing is pulling on you. What we call gravity is the shape of space and time, bent by the presence of matter and energy. And objects moving through that bent geometry follow the straightest path available to them. The Earth is not tugging the moon. The Earth has put a dent in the geometry, and the moon is going straight ahead through a dented region. The usual picture is a bowling ball on a stretched rubber sheet. It is a bad picture in about 4 different ways, but it gets one thing across. Matter tells space how to curve. Curved space tells matter how to move. That is the whole idea, and everything after this depends on it. Now, Einstein had built a machine for describing how geometry responds to matter, and the obvious thing to do with a machine like that is to feed it everything. Not a star, not a solar system, the universe. All of it, treated as one object. So in 1917, he did exactly that in a paper called Cosmological Considerations in the General Theory of Relativity. He got an answer he did not want. The equations told him the universe could not sit still. This is worth pausing on because it is the hinge that everything else turns on. Fill space more or less evenly with matter and let gravity do what gravity does. And the whole arrangement has to move. It has to collapse inward under its own weight, or it has to fly apart. There is no stable middle option. A universe at rest is like a pencil balanced on its point. In principle, you can place it there. In practice, the smallest disturbance ends it. Einstein did not believe that. Nobody believed that. And why would they? What evidence was there in 1917 that anything at all was moving? The observed universe in 1917 was the Milky Way, and the Milky Way looked calm. The stars had been in the same constellations since the Babylonians. There was no hint anywhere in the sky that anything was moving on a grand scale. The universe was obviously static. Everyone knew that. It was as settled as any fact in science. So Einstein did something he would spend the rest of his life being uncomfortable about. He changed the equations. He added a term, a constant, sitting in the geometry itself, representing a kind of tension in empty space that pushes outward everywhere at once. He gave it the Greek letter lambda and called it the cosmological constant. He tuned it to exactly the value needed to balance the inward pull of all the matter so the universe would hold still. It worked. Sort of. He got his static universe. But it was the pencil on its point again, balanced rather than stable. And if you nudged it even slightly, it would run away in one direction or the other. Einstein either did not notice that or chose not to dwell on it. Then, within months, the thing began to unravel. A Dutch astronomer named Willem de Sitter, working in Leiden, took Einstein's modified equations and asked what happens if you keep the lambda term but remove all the matter. An empty universe with tension in it. It should have been a pointless exercise, a mathematician's toy. It expanded. De Sitter's empty universe stretched, and anything you placed in it would drift apart from everything else. He published in 1917, and for years afterward, people argued about what it actually meant, because the mathematics of the era made it genuinely difficult to tell whether the drifting was real or an artifact of how you had chosen your coordinates. There is a whole literature on this, and it is dense, and most of it is now a historical curiosity. But it did one important thing. It planted the idea that the equations of general relativity might permit a universe that moves. Einstein disliked that intensely. He spent a good deal of effort trying to argue that de Sitter's solution was unphysical. And this is the part of the story that gets flattened in most tellings, so it is worth being straight about. The Big Bang was not proposed by somebody who wanted it. It was forced out of the mathematics, repeatedly, against the wishes of nearly everyone involved, over about 15 years. Einstein resisted it. Eddington resisted it. Hubble, who provided the crucial evidence, never fully accepted the interpretation. The universe kept insisting, and one by one, mostly slowly, people gave in. The first person to take the mathematics at face value was a Russian meteorologist. He is the most quietly tragic figure in the whole account. Alexander Friedmann was born in St. Petersburg in 1888, the son of a ballet dancer and a musician. He fought in the First World War as a bombardier in the Russian Air Service, flying reconnaissance and dropping bombs on the Austrian front, and by his own account, working out ballistics corrections in the air. He survived that, survived the revolution, survived the famine years, and ended up in Petrograd working on the mathematics of the atmosphere, weather prediction, essentially, fluid dynamics on a rotating sphere. So what does a weather mathematician do with a theory of gravity? He treats it the way he treats the atmosphere. He was not a cosmologist. He got hold of the papers on general relativity late. He approached them the way a fluid dynamicist would, which turned out to be exactly the right instinct. In 1922, he published a paper called On the Curvature of Space, and what he did in it was refuse to assume the answer. Everyone else had started by insisting the universe was static and then working out what conditions would allow that. Friedmann did the reverse. He solved Einstein's equations for a universe filled evenly with matter and let the solutions be whatever they were. He found a family of them, not one universe, a set. Some expand forever, slowing down but never stopping. Some expand, slow, halt, and collapse back inward. One sits exactly on the boundary between those two behaviors, expanding at precisely the rate needed to just barely escape. And in several of them, if you run the mathematics backward in time, the entire thing shrinks toward a moment where the density becomes infinite and the equations stop returning meaningful answers. Friedmann had derived the expanding universe in 1922, 7 years before anybody measured it. He did not claim it was the real universe. He was careful about that, and he was writing as a mathematician, exploring what the theory permitted. But the possibility was now on the page in black and white, published in a respectable German journal, and it was correct. Einstein read it and rejected it. He wrote a short note to the same journal saying Friedmann's results were suspicious and that the calculations contained an error. It was a public dismissal, brief and confident, from the most famous scientist alive, and it was wrong. Einstein had made the mistake himself. Friedmann found out and wrote to him. A careful letter, laying out the derivation step by step, asking Einstein to look again. Einstein was traveling and did not see it for months. A mutual acquaintance eventually cornered him and walked him through the mathematics in person. Einstein checked. Friedmann was right. And to his credit, he published a retraction, saying that he had been mistaken and that Friedmann's results were correct and clarifying. It is a short note. It is also, when you know what it cost him, a rather decent thing to have written. Friedmann never got to do anything with it. In the summer of 1925, he took a balloon flight to a record altitude of around 7,000 meters, taking meteorological measurements. Shortly after, he fell ill. The diagnosis was typhoid fever, most likely from a pear he had bought on a trip to Crimea, though the balloon flight has always been part of the story too. He died in September of 1925. He was 37 years old. He had published the correct mathematical description of an expanding universe, been publicly told he was wrong by Einstein, been vindicated, then died 4 years before Hubble's observations proved him right about the actual sky. His name is on the equations. Nearly every cosmology course in the world teaches the Friedmann equations in the first fortnight. He did not live to know that. And the second person to derive the expanding universe did it independently, 5 years later, without having read Friedmann at all. He was a Belgian priest. Georges Lemaitre was born in Charleroi in 1894. He served in the Belgian army through the First World War as an artillery officer, was decorated for bravery, and came out of it and went straight into a seminary. He was ordained in 1923. He was also, at the same time, a very good mathematical physicist. He never seems to have felt any tension between the two occupations at all. He studied under Arthur Eddington in Cambridge, spent a year at Harvard, took a doctorate at the Massachusetts Institute of Technology, and went back to Belgium to teach at Leuven. In 1927, he published a paper with an unwieldy title, in French, in a journal called Annales de la Société Scientifique de Bruxelles. If you were an astronomer anywhere outside Belgium, you almost certainly did not read that journal. Almost nobody did. In it, Lemaitre derived the expanding universe from Einstein's equations, exactly as Friedmann had, without knowing Friedmann's work existed. But he did something Friedmann had not. He connected it to actual data. The astronomers had been collecting spectra of faint fuzzy objects in the sky for over a decade. Vesto Slipher, at the Lowell Observatory in Flagstaff, Arizona, had been doing it since 1912, one exhausting exposure at a time, sometimes leaving a photographic plate open for 20 or 30 hours across multiple nights to gather enough light. And what he found was that almost all of those objects showed their spectral lines shifted toward the red end. By 1925, he had measured around 40 of them, and something like 36 were shifted red, which conventionally meant moving away. Nobody knew what to make of that. Slipher, who deserves far more credit than he generally gets, published it and largely left the interpretation to others. Lemaitre took Slipher's redshifts, combined them with the best distance estimates available at the time, and worked out something remarkable. The further away an object was, the faster it appeared to be receding, and the relationship between those two numbers was roughly a straight line. He calculated the slope of that line. He got a value of about 625 kilometers per second for every megaparsec of distance. That number is far too high, and we will come back to why. But he had it. 2 years before Hubble published essentially the same relationship, Lemaitre had derived it theoretically, tested it against the available data, and stated a rate. He sent the paper to Einstein. They met at the Solvay conference in Brussels in October of 1927, one of those photographs where 17 of the 29 people in the frame have a Nobel Prize. Lemaitre described the work, and Einstein, according to Lemaitre's own account of it afterward, told him that his calculations were correct, but that his physics was abominable. That line has been repeated for nearly a century. It is worth noting that we only have it from one side, but it is entirely consistent with everything else Einstein said and wrote about expanding universes at that time, so there is no strong reason to doubt it. Lemaitre went back to Belgium. The paper sat unread in its obscured journal for 4 years. Then, in 1930, Eddington, who had taught Lemaitre in Cambridge and had forgotten receiving a copy of the paper, was in a meeting of the Royal Astronomical Society, where the problem of the unstable static universe was being discussed. Lemaitre saw the report of that meeting, wrote to Eddington, and pointed out that he had solved it 3 years earlier. Eddington read it properly this time, realized what he had been sitting on, and was mortified. He arranged for an English translation to appear in the monthly notices of the Royal Astronomical Society in 1931. He began promoting the work energetically. There is a footnote to that translation which caused an argument lasting about 80 years. In the English version, the paragraphs containing Lemaitre's calculation of the expansion rate are missing. For decades it was assumed that somebody had cut them to protect Hubble's priority. And this was treated as a minor scandal. Then in 2011, the original correspondence was tracked down. Lemaitre had done the translation himself, and he had removed his own paragraphs, because by then Hubble had published better data, and Lemaitre saw no reason to reprint superseded numbers. He simply did not care about the credit. That is either admirable or slightly maddening, depending on your temperament, and it is very much in character. Then, in 1931, Lemaitre took the step that nobody else was willing to take. If the universe is expanding, he wrote, then run it backward. Yesterday, everything was closer together than today. 1,000 years ago, closer still. Keep going. There must have been a moment when all of it was compressed into a single quantum state. He called it the primeval atom, and sometimes the cosmic egg, and he described the present universe as the fragments of a firework display, with the faded remains of the original brilliance still hanging in the sky. He published it in Nature, in a letter of about 800 words. It is the first serious proposal of what we now call the Big Bang, and it came from a Catholic priest working in Leuven. It was met with a great deal of discomfort. Some of that discomfort was scientific. It looked suspiciously tidy. A universe with a beginning, proposed by a clergyman, was going to attract exactly the objection you would expect, and it did. And Lemaitre spent years pushing back against it. He was consistent about this, and quite firm. He held that the primeval atom was a physical hypothesis to be judged on physical evidence, and that it neither supported nor contradicted any religious position, and that mixing the two did damage to both. When Pope Pius XII gave a speech in 1951 appearing to endorse the theory as confirmation of creation, Lemaitre was privately unimpressed and worked quietly through channels to discourage any repeat of it. He did not want his cosmology drafted into an argument it could not settle. So by 1931, the theory existed. It had been derived twice independently. It matched the available observations. What it still lacked was a reliable way of knowing how far away anything actually was. That problem was cracked open by a woman who was paid 25 cents an hour and was not permitted to operate a telescope. Come inward for a moment, to a room in Cambridge, Massachusetts, in the early 1900s. The Harvard College Observatory had a problem that was, in its way, the same problem as everybody else's. Photographic plates, hundreds of thousands of them, glass, each one a long exposure of a patch of sky, stacking up faster than anyone could examine them. Somebody had to measure the position and brightness of every star on every plate, by eye, with a magnifying glass, and record it. The director, Edward Pickering, hired women to do it. He hired them because they would work for a fraction of what men were paid. And this was stated openly at the time, and was not considered controversial. They were called computers, which was a job description before it was a machine. Around 80 women passed through that room over the years. Some were college graduates in astronomy who had no other route into the field at all. Henrietta Leavitt arrived as a volunteer in 1895 after graduating from what would become Radcliffe College. She had contracted an illness that left her increasingly deaf. She joined the paid staff in 1902 at 30 cents an hour, which was slightly above the rate, in recognition of the quality of her work. Her assignment was variable stars, stars that change brightness on a cycle. She was given plates of the small Magellanic Cloud, a hazy patch visible from the southern hemisphere, photographed from Harvard Station in Arequipa, Peru. Her job was to find variables in it and catalog them. She found around 1,800. In going through them, she noticed something that nobody had asked her to look for. There is a class of variable star called a Cepheid, named after the star Delta Cephei. They pulse. They swell and contract on a regular cycle, brightening and dimming, and the cycle is reliable enough to set a clock by. Some run through it in a day. Some take 2 months. What Leavitt saw in 1908 and then far more precisely in 1912 was that the brighter Cepheids had longer cycles, and not vaguely. Plot the brightness against the logarithm of the period, and the points fall on a straight line. And why does that matter? What use is a correlation between brightness and pulse rate? Now, ordinarily, a star's apparent brightness tells you nothing useful, because a faint star might be dim and near or brilliant and far. The two are hopelessly tangled. But every star in the small Magellanic Cloud is at essentially the same distance from us, because the cloud is far away and compact compared to that distance. So within that one group, differences in apparent brightness are differences in real brightness. The distance cancels out, which meant Leavitt had found the thing astronomy had been missing since the beginning. A way to know how bright a star truly is from the outside just by timing it. Find a Cepheid anywhere in the sky. Time its pulse. That tells you its true brightness. Compare that with how bright it looks. The difference between those two numbers is caused by distance and distance alone, and you can solve for it. She had built a measuring stick that reached beyond the Milky Way. Her paper on it, published under Pickering's name in the Observatory Circular, with a note stating that the work was prepared by Miss Leavitt, runs to about 3 pages. She was not allowed to follow it up. Pickering directed her onto other tasks, standardizing photographic magnitudes, which she did superbly, and which was not the same thing. She died of cancer in 1921 at 53 in Cambridge. In 1925, a Swedish mathematician wrote to Harvard intending to nominate her for the Nobel Prize, and was informed that she had been dead for 4 years. The prize is not awarded posthumously. Almost everything that follows in this story is measured with her ruler. The first person to use that ruler seriously was Harlow Shapley. He used it to make one enormous correct discovery and one enormous mistake, both at the same time. Shapley grew up in Missouri, left school after the 5th grade, worked as a crime reporter in Kansas, and went back into education late. The story he told about choosing astronomy was that he arrived at university intending to study journalism, found the course had been postponed a year, opened the catalog of subjects, and picked the first one he could pronounce. Archaeology defeated him. Astronomy was next on the list. It is a good story, and he told it often. By 1918, he was at Mount Wilson in California, working with the 60-inch telescope, and he applied Leavitt's relation to the globular clusters. These are dense balls of hundreds of thousands of old stars scattered around the Milky Way. Shapley measured Cepheids in them, worked out their distances, and mapped where they sat. They were not centered on us. They were centered on a point in the direction of Sagittarius, tens of thousands of light years away. which meant the sun is not at the middle of the galaxy. We are out in the suburbs, a long way from the center, on an unremarkable arm. That was a genuine displacement, the same kind Copernicus had delivered, and Shapley got it right. He also concluded that the Milky Way was far larger than anyone had thought, which was also right. Then he overreached. Because his Milky Way was so vast, Shapley decided it must be the entire universe. The spiral nebulae, those faint pinwheels of light that Slipher had been taking spectra of, must be gas clouds inside our own galaxy. Nothing lay beyond. Not everybody agreed. Heber Curtis at Lick Observatory thought the spirals were separate galaxies in their own right, island universes, each one comparable to the Milky Way, unimaginably far away. In April of 1920, the two of them argued it out in the auditorium of the Smithsonian Museum of Natural History in Washington. It is remembered as the Great Debate, though it was really 2 lectures and a discussion. And by most accounts, Curtis was the better speaker on the night. So which was it? Was the Milky Way the whole of existence, or one island among countless others unimaginably far apart? Neither man won. They could not win, because the evidence needed to settle it did not exist yet. It arrived 3 years later, on a photographic plate, from a man with a pipe, a fabricated war record, and an accent he had invented himself. Edwin Hubble is not a straightforwardly likable figure. He was from Missouri, went to the University of Chicago, won a Rhodes Scholarship to Oxford, and came back speaking in an English accent that he kept for the rest of his life, and that startled everybody who had known him before. He claimed to have practiced law in Kentucky, which appears not to have been true. He implied he had seen combat in France, which he had not. He was competitive to the point of unpleasantness about credit. He was also an outstanding observer, patient, meticulous, and he had access to the best instrument on the planet. The 100-inch Hooker telescope on Mount Wilson, above Pasadena, had been finished in 1917. It was the largest in the world and would remain so for 30 years. The mirror weighed 4.5 tons. Observing meant sitting in an unheated cage in the freezing dark of a Californian mountain, hand guiding the instrument for hours to keep a single object fixed on a glass plate. On the night of the 5th of October, 1923, Hubble photographed the Andromeda Nebula. He was looking for novae, stars that flare up suddenly. He found 3 candidates and marked them on the plate with an N. Then he checked one of them against earlier plates of the same region. It had not flared once. It was going up and down on a cycle, around 31 days. It was a Cepheid. On the original plate, you can still see what he did. He crossed out the letter N and wrote VAR for variable and put an exclamation mark after it. That exclamation mark is one of the few completely undisguised moments of feeling anybody has ever left in the Mount Wilson archive. Because he knew immediately what it meant. He had Leavitt's relation. He had the period. He could get the true brightness, compare it to the apparent brightness, and solve for the distance. He got about 900,000 light years. Far too small, as it turns out, by a factor of about 3, for reasons nobody could have known at the time. But it did not matter, because even at 900,000 light years, Andromeda was hundreds of thousands of light years outside anything Shapley claimed the Milky Way could be. Andromeda was not a cloud in our galaxy. It was another galaxy, full of stars, comparable in size to our own, unthinkably distant. Hubble wrote to Shapley with the result. Shapley read the letter, handed it to a graduate student standing nearby, and said that this was the letter that had destroyed his universe. To his credit, he accepted it more or less at once, and with that, the universe got bigger in a single step than it ever had before, or has since. Every one of those thousands of faint smudges catalogued as nebulae was a separate galaxy, each with its own hundreds of billions of stars. The Milky Way went from being everything to being one item in a catalog. Hubble then set about measuring as many of them as he could, and here is where the second man comes in. He is the one worth remembering. Milton Humason had dropped out of school at 14. He worked as a mule driver, hauling equipment up the trail to the Mount Wilson site during construction. Then he took a job at the observatory as a janitor. Then he was promoted to night assistant, and it turned out he had extraordinary hands. He could guide the telescope for 6 or 8 hours without losing the object, night after night, which is a physical skill and a temperamental one, and cannot really be taught. He became one of the finest observers of the century, with no formal education past the age of 14 at all. Humason took the spectra. This is the exhausting half of the work. To split the light of a faint galaxy into its component colors, you need an enormous exposure. He would open a plate on one galaxy and sit with it across several nights in the cold, closing the shutter at dawn and reopening it the following evening, sometimes for over 30 hours of accumulated time on a single object. And in every spectrum, the pattern was the same. The dark absorption lines from familiar elements were present in their familiar relative spacings, but the entire set was slid toward the red. Hubble had the distances from the Cepheids. Humason had the velocities from the shifts. In 1929, Hubble published a paper plotting one against the other, with about 24 galaxies on it. It is a straight line, a scattered, noisy straight line, on a graph small enough to fit in your hand. It is one of the most consequential images in the history of science. The further away a galaxy is, the faster it recedes, in direct proportion. That relation is now called Hubble's law, or, since 2018, and a vote of the International Astronomical Union, the Hubble-Lemaitre law, which is a fairer name and is slowly catching on. His number for the rate was about 500 kilometers per second per megaparsec. The modern figure is somewhere near 70. He was off by a factor of 7. How does that happen, with the best telescope on Earth and years of careful work? And why did it take 2 decades to catch? The reason is worth a minute, because it is a very human sort of error. There are 2 kinds of Cepheid variable, with different underlying physics and different brightness relations. And nobody discovered that until Walter Baade did in the 1940s, using the wartime blackout over Los Angeles to get unusually dark skies. Hubble had been calibrating with one type and measuring with the other. On top of that, some of the objects he took to be single bright stars in distant galaxies were actually whole clusters of stars blurred together, which made those galaxies look much closer than they were. The consequence was embarrassing. If you take Hubble's rate and run the expansion backward, you get an age for the universe of about 1.8 billion years. Meanwhile, the geologists, using radioactive decay in rocks, were confidently dating the Earth at over 3 billion years and rising. The universe was younger than the ground you are standing on. So how do you defend a theory like that? What do you say to a geologist holding a rock that predates your entire cosmos? That was the state of the field for roughly 2 decades. It was used, quite reasonably, as an argument that the whole expanding universe picture had to be wrong somewhere. It took until the 1950s for the distance scale to be corrected and the ages to fall into line. And Hubble himself, for the rest of his life, was careful never to fully commit to the interpretation. He would say that the redshifts behaved as if they were velocities. He wrote about the apparent velocity displacement. He kept the door open for some other cause of the shift, some unknown process that reddened light over long distances. He measured the expansion of the universe and declined to call it that. So we now have the two pieces: a theory that says the universe cannot sit still, and an observation showing that it is not sitting still. Which brings us to the first genuinely confusing thing, and it is the one that trips up nearly everybody, including a fair number of people who work in physics. Because when you hear that distant galaxies are rushing away from us, there is an obvious picture that forms, and the obvious picture is wrong. Let's take it slowly. The everyday version of a redshift is a Doppler shift, and you have heard one thousands of times. An ambulance passes you, and the pitch of the siren drops. While it is approaching, the sound waves arrive squeezed together, so the pitch is higher. Once it is passed, they arrive stretched out, so the pitch drops. Nothing has changed about the siren. Only the relationship between the source and you has changed. Light does the same thing. A source moving toward you has its waves compressed, shifting the light bluer. A source moving away has its waves stretched, shifting it redder. This is real. It is measured constantly, and it is how we detect planets around other stars and track binaries. So the natural reading of Hubble's result is that all those galaxies are flying away from us through space, like fragments from a grenade. We are sitting near where the grenade went off. That picture gets almost everything wrong. The galaxies are not, for the most part, moving through space at all. They are sitting more or less still, where they have always been. What is happening is that the space between them is getting bigger. Read that again, slowly, because it is the whole thing. The distance between two galaxies increases without either galaxy going anywhere. Space is not an empty container that things move around inside. Space is a participant. It has geometry. That geometry can change over time, and what general relativity permits. And Friedmann and Lemaitre proved is that the scale of it can grow. The light did not get stretched because the source was running away. The light got stretched because the space it was crossing expanded while it was in transit. Think about what that means for a photon leaving a distant galaxy. It sets out toward us, a wave of a particular length, and it travels for, say, 10 billion years. Over that time, the space it is passing through swells, and the wave swells with it, because the wave is a feature of the space. It arrives longer than it left. Redder. The redshift of a distant galaxy is not a speedometer reading. It is a record of how much the universe has stretched since that light was emitted. When astronomers say a galaxy has a redshift of 1, they mean the universe has doubled in scale since that light set out. Not that the galaxy is moving at any particular speed, that the container has doubled. Once you have that in your head, the second confusion dissolves, or at least becomes answerable. If everything is rushing away from us, are we in the middle of it? We are not. And the reason we are not is one of the more satisfying pieces of reasoning available in this subject, so let's do it properly. Imagine a long strip of elastic laid out on a table, with beads glued along it at even spacing, say a centimeter apart. The beads are stuck fast. They cannot slide. Now take both ends of the elastic and stretch it until it is twice as long. Sit on any bead you like and look around. Its immediate neighbor, which was 1 centimeter away, is now 2 centimeters away. It has moved 1 centimeter. The bead 2 along was 2 centimeters away and is now 4, so it has moved 2. The bead 10 along was 10 centimeters away and is now 20, so it has moved 10. The further a bead was, the further it went, in direct proportion to its starting distance, which is Hubble's law exactly, and it has appeared without anybody moving through the elastic, and without any bead being special. Here is the part that matters. Move to a different bead and do the whole exercise again. You get the identical result. Every bead sees every other bead receding, and the recession speed rising with distance. And every bead has an equally good case for calling itself the center, which means none of them is. The recession you observe from Earth is not evidence that Earth is anywhere in particular. An astronomer in a galaxy 12 billion light-years from here, looking back at the Milky Way, sees us tearing away from them at enormous speed and sees their own neighborhood as perfectly calm. Both of you are right. Neither of you is at the middle, because on a stretching elastic, there is no middle to be at. The usual upgrade to this picture is the surface of a balloon with dots inked on it. Inflate the balloon, and every dot moves away from every other dot, with no dot at the center of the surface. That is a good analogy, and it fails in one specific way that matters, so it is worth naming the failure rather than letting it sit there. A balloon has an inside. It has a center, in the ordinary sense, at the middle of the volume of air. It is expanding into the room around it. The universe does not have that. The analogy only works if you agree to live entirely on the rubber, in 2 dimensions, with no awareness of anything off the surface, and no inside and no outside existing at all. The surface is all there is, which is a genuinely difficult thing to hold in mind. If it slips away from you, that is not a failure of understanding. It slips away from everybody. It is fair to ask how we know the elastic is evenly beaded in the first place. How would you even check? You cannot travel to another galaxy and look around from there. The whole argument rests on the assumption that the universe is broadly the same everywhere, with no special locations, and that assumption has a name. It is called the cosmological principle, and for a long time it was exactly that, a principle, meaning an article of faith adopted because the alternative was unworkable. It is now measured, and it holds up rather well. The evidence comes in 2 parts. The first is that the universe looks the same in every direction from here, which is called isotropy, and the microwave background establishes it to 5 decimal places. Nothing else in nature is that uniform. The second part is harder, because we cannot travel anywhere to check whether it looks the same from elsewhere. What we can do is survey enormous volumes of galaxies and see whether the distribution settles down. It does. On scales below about 300 million light-years, the universe is extremely lumpy, full of clusters and filaments and voids. Above that scale, take any large box anywhere and count what is inside it, and you get the same answer as any other box. The lumpiness averages out. There have been reports of structures too large for that to be comfortable, enormous groupings of distant quasars spanning billions of light-years. They generate periodic headlines about the cosmological principle being in trouble. The usual resolution is that such features are marginal statistically, and that if you go looking for patterns across a whole sky, you will find some. It is not fully settled, but the working position, supported by the surveys, is that the universe is homogeneous once you stand far enough back, and everything in modern cosmology depends on that being true. But it goes straight to the next confusion, which is probably the single most common question about all of this. What is the universe expanding into? If it is getting bigger, surely it must be getting bigger inside something. There has to be room being taken up. Where is the space it is expanding into? What is out there, at the edge? The answer is that there is no edge, and there is nothing out there, and this is not a dodge. It is a specific consequence of what general relativity actually says about geometry. It took mathematicians most of the 19th century to make it precise. There are 2 ways a thing can be curved or stretched. The first is the intuitive one. A ball is curved, and you can see that it is curved because you are standing outside it, looking at it, sitting in the larger space it occupies. That is called extrinsic curvature. It is curvature described from outside. The second kind can be measured entirely from within, by somebody trapped on the surface, with no access to anything beyond it and no ability even to imagine an outside. Suppose you live on a very large sphere and you have never left it. You can still discover it is a sphere. Draw a large triangle by walking 3 straight lines. Measure the interior angles. On a flat surface, they sum to 180 degrees. On a sphere, they sum to more. Or take a circle, measure the distance around it and the distance across it, and check whether the ratio is what geometry on a flat sheet says it should be. On a sphere, it is not. You never leave the surface. You never look at it from outside. You have measured the curvature from within, using nothing but a ruler. That is intrinsic curvature, and Carl Friedrich Gauss and then Bernhard Riemann built the mathematics of it in the 1820s through the 1850s, decades before there was any physical use for it. Riemann's habilitation lecture in 1854, delivered to a faculty audience that included Gauss, and by all accounts baffled most of the rest of the room, laid out geometry in any number of dimensions with curvature defined entirely internally. Einstein's field equations are written in Riemann's language. Every statement general relativity makes about the shape of space and time is intrinsic. The theory describes the geometry from the inside, and it contains no reference to any embedding space whatsoever, not because physicists decided to leave one out, because the equations do not have a slot for one. So when we say the universe is expanding, the statement is about a scale factor inside the geometry. Distances measured between points, using rulers that live in the universe, get larger over time. That is the entire content of it. There is no exterior region being colonized. Asking what it expands into is like asking what direction is north of the North Pole. The question is grammatically fine, and it does not correspond to anything. You have taken a word that means something within a system and applied it outside the system, where it stops meaning anything at all. And this is the point at which the name starts actively causing damage. So let's deal with the name now. The Big Bang was not an explosion. An explosion is a thing that happens at a location. There is a center, there is material. The material flies outward through the surrounding space into regions that were previously empty. There is a shock wave with an inside and an outside. If you are far enough away, you can watch it from a distance. Nothing in that description applies here. There was no center, because there was no space outside for a center to be defined against. There was no surrounding region to expand into. Nothing flew through anything. There was nowhere to stand and watch. What happened is that space itself, everywhere, all of it at once, was extremely dense and extremely hot, and then it expanded, not from a point into a void, everywhere, simultaneously, becoming less dense, which produces the third great confusion, and it is my favorite one, because the answer is genuinely startling and completely true. Where did the Big Bang happen? It happened where you are lying right now. It also happened at every other location in the universe at the same time. The Big Bang was not an event at a place. It was a condition of every place. The room you are in, the space occupied by your bed, the air above your face, all of that was part of the hot, dense state. So was the space currently occupied by the Andromeda Galaxy, and the space 13 billion light-years away in the direction of Ursa Major, and every other cubic centimeter in existence. If you could rewind the film, You would not see everything rushing toward a spot in the distance. You would see the room getting smaller, the distance between your walls shrinking, the distance between every pair of particles anywhere shrinking, all together, everywhere at once, until the density everywhere became unmanageable and the description broke down. That is what running the expansion backward means. Not a collapse toward a point in the room, a shrinking of the room itself, and of every room, and of the space between rooms. There is a further wrinkle here that trips up even people who have accepted all of the above. If the universe is infinite in extent now, and the current evidence is at least consistent with that, then it was infinite then too. An infinite thing that shrinks is still infinite. Have every distance in an endless space, and you have an endless space with everything closer together. Do it 1,000,000,000,000 times over, and it is still endless. The Big Bang, in that case, was not a small thing that got large. It was an infinite thing that was dense and became less dense. We say the observable universe was once the size of a grapefruit or a proton or whatever the comparison of the week is. That is a fair statement about the observable part, the sphere of stuff whose light has had time to reach us. It is not a statement about the whole. The whole may well have no size to quote at all. Nobody knows which of those is true. The measurements say space is flat to within a fraction of a percent, and a flat universe with the simplest topology is infinite, but the error bars leave room for a very large finite one that just looks flat because we are seeing a small patch of it, in the same way a field looks flat to somebody standing in it. Now, at this point, it is fair to ask where the name came from, if it is so misleading. The answer is that it came from somebody who did not believe a word of it. Fred Hoyle was one of the most gifted and most stubborn scientists of the 20th century. Yorkshire, working class, largely self-taught in his early years, having decided as a child that school was a waste of his time and having simply stopped attending for long stretches. He got to Cambridge, worked on radar during the war, and became one of the great astrophysicists of the century, and also one of the great holders of losing positions, and he held several of them until his death. On the 28th of March, 1949, Hoyle gave a talk on the BBC Third program. He was an outstanding broadcaster, one of the first genuinely popular science voices on radio. He was explaining the competing pictures of the universe. In describing the rival theory, the one where everything begins in a dense state, he referred to the hypothesis that all the matter in the universe was created in one big bang at a particular time in the remote past. That is the moment. That is where the name enters the language. In a radio talk, from a man describing an idea he thought was wrong. For decades afterward, it was assumed the phrase was a sneer. Hoyle always denied it, and said repeatedly that he had been reaching for a vivid image for a listening audience with nothing but sound to work with, and that he needed a contrast between his own picture, which was smooth and continuous, and the sudden one. Historians who have gone back to the transcripts mostly side with him. The tone reads as descriptive. The scorn came later, and there was plenty of it later. The name stuck because it was memorable, which is the only reason names ever stick. Nobody has managed to shift it since. In 1993, the magazine Sky and Telescope ran a competition to rename the theory, and received over 13,000 entries from 41 countries. The judges, who included Carl Sagan, declined to choose a winner. Not one of the 13,000 was better than the term coined by the theory's most determined opponent on the radio, and Hoyle had an alternative. It is worth understanding because it was a serious theory, and for about 15 years it was genuinely competitive. The reason it lost is the reason the rest of this story exists. The steady-state theory came out of a conversation between three men in Cambridge in 1946, and out of a horror film. Hoyle, Herman Bondi, and Thomas Gold had all worked together on radar during the war and had stayed close afterward. Bondi and Gold were both Austrian, both Jewish, both had left ahead of the annexation, and both had been interned by the British as enemy aliens for a period before being released and put to work on the war effort, which is one of the odder administrative decisions of the era. The three of them went to see a film called Dead of Night. It is an anthology of ghost stories, and its structure is circular. The final scene loops back into the opening scene, so the film has no true beginning and no true end. You could join it at any point, and it would be the same film. Gold came out of the cinema and asked whether the universe might be like that. The problem they were trying to solve was real, and it was serious. The expanding universe of the 1940s had that terrible age problem we talked about. Hubble's rate gave the universe less than 2 billion years, and the rocks under everyone's feet were older than that. Something in the picture had to be wrong. Their solution was to keep the expansion and throw out the beginning. The universe expands, yes. Galaxies do recede. But as the space between them opens up, new matter comes quietly into existence in the gaps at an extremely slow rate and condenses into new galaxies. The overall density never changes. Look at the universe at any epoch and it looks the same. No beginning, no end, no age problem. Because there is no age. They called it the perfect cosmological principle. The ordinary cosmological principle says the universe looks the same from every place. The perfect version adds that it looks the same at every time. The rate of creation required is almost comically small. About 1 hydrogen atom per cubic meter every billion years or so. That is far below anything that could have been detected then or now. It is not a wild proposal in terms of quantity. It is a wild proposal in terms of principle, and the steady-state people knew it, and their defense was sharp. You are asking us to accept matter coming into being from nothing, they said. Fine. But your theory has all the matter in the universe coming into being from nothing, in one instant, and calls that respectable. At least ours is spread out politely over time. So which is the stranger claim? 1 atom appearing per cubic meter per billion years, forever? Or every atom in existence appearing at once and never again? That is a good argument. It is not a knockdown, but it is a good argument, and for about 15 years the field was genuinely split. Steady state was the dominant view in Britain. The evolving universe was stronger in the United States and the Soviet Union, and there was real animosity in it. Hoyle was not gracious about opponents, and neither were several of them about him. What settled it was that one of the two theories made a prediction it could not take back. Which brings us to George Gamow, who is one of the few people in this whole account who seems to have been having an unambiguously good time. Gamow was born in Odessa in 1904. He studied in Leningrad, worked in Göttingen and Copenhagen and Cambridge with the founders of quantum mechanics. In 1928, explained how alpha particles escape from atomic nuclei by quantum tunneling, which was a major result and would have been enough for one career. He then tried repeatedly to defect from the Soviet Union. His first attempt, with his wife, was to paddle a kayak across the Black Sea to Turkey, roughly 250 kilometers, with supplies including boiled eggs, chocolate, and brandy. They were driven back by weather after a day and a half. A second attempt from Murmansk to Norway also failed. He eventually got out legally in 1933 by being permitted to attend the Solvay conference in Brussels with his wife and simply not returning. He landed at George Washington University in Washington, and he was a serious physicist with an extremely unserious surface. He wrote popular books full of his own cartoons. He played practical jokes on colleagues that were sometimes elaborate enough to alarm them. And in the 1940s, he asked a question that nobody had properly pushed on. If the universe really was once hot and dense, what would that have done to the matter in it? The reasoning is direct. Compress a gas, and it heats up. Run the expansion backward, and the early universe was not just crowded, it was searingly hot. Hot enough that atoms could not hold together. Hot enough that nuclei could not hold together. A soup of bare protons, neutrons, electrons, and radiation. Now let it expand and cool. As it cools, protons and neutrons can start sticking. Nuclear fusion in the open, everywhere at once, for a brief window before expansion thins everything out too much to continue. Gamow set his graduate student Ralph Alpher to work out what came out of that furnace. The result is a paper published on the 1st of April, 1948, in Physical Review. It is Alpher's work and Gamow's supervision, and Gamow, unable to resist, added the name of his friend Hans Bethe to the author list so that the paper would read Alpher, Bethe, Gamow, which sounds like alpha, beta, gamma. Bethe had not worked on it. He agreed to be included. Gamow appears to have found this funny for the rest of his life, and Alpher, whose doctoral work it was not entirely delighted to have his sole authorship diluted for a pun. What the paper found, and what Alpher and Robert Herman refined over the following years, is a set of numbers that turn out to be one of the strongest pieces of evidence in all of cosmology. The early universe should have produced hydrogen and helium and very little else. Specifically, about 3/4 hydrogen by mass and about 1/4 helium, plus a trace of deuterium, which is hydrogen with a neutron attached and a whisper of lithium. That is what we see. The modern figure for the helium fraction of ordinary matter in the universe is close to 24% by mass, and it is remarkably uniform. You find it in gas clouds that have never been near a star. You find it in the oldest, most pristine material available. Stars do make helium, but stars have not been running long enough or efficiently enough to make anything like that quantity. And the places with the fewest stars still have it. Something made an enormous amount of helium before there were any stars. That is a hard fact, and steady state had no good answer for it. The window for all this is narrow, and it is worth pausing on how narrow, because it is one of the more astonishing coincidences of scale in physics. Nuclear fusion could not begin until the universe was cool enough that the newly formed nuclei were not immediately blasted apart again, which took roughly a minute or two. It had to stop once expansion had spread everything so thin that particles stopped finding each other, which took about 20 minutes total. Every helium nucleus in your body, in the sun, in the atmosphere of Jupiter, was made in that 20-minute window. And there has been nothing like it since. The chain runs upward and then it stops. 2 protons and 2 neutrons make helium-4, and helium-4 is extraordinarily stable. To build heavier things, you want to add another proton or another helium nucleus to it, and there you hit a wall, because there is no stable nucleus with 5 particles in it. There is no stable nucleus with 8. Both of those slots are empty. The latter has 2 missing rungs in a row, right at the point where you need them, and anything that forms there falls apart in a tiny fraction of a second. So the early universe could not make carbon. It could not make oxygen, or nitrogen, or iron, or calcium, or any of the things you are largely built from. It made hydrogen and helium and a rounding error, and then the door closed. So where did everything else come from? Where did the calcium in your teeth come from? Or the iron in your blood? Or the carbon in your hands? Which left a very large hole in the theory, and the man who filled it was Fred Hoyle. This is the part of the story that I find genuinely moving, and it does not usually get told alongside the rest. Hoyle wanted to prove there was no beginning, so he needed to show that everything heavy could be made inside stars over time without any special early epoch. He worked on this for years, and in 1954, he published a paper on the synthesis of elements in stellar interiors that is one of the great papers of the century. The problem was the same missing rungs. To get past helium, you need to fuse 3 helium nuclei into carbon. The odds of 3 of them meeting simultaneously are effectively 0, because the intermediate step, 2 heliums making beryllium-8, falls apart in about 1/10 of a millionth of a billionth of a second. Hoyle reasoned backward from the fact that carbon exists. He was made of carbon. Therefore, the process must work. Therefore, there must be something making it work. And he predicted that the carbon nucleus must have a specific excited state, at a specific energy, that would let the reaction resonate and proceed far faster than the naive calculation allowed. He put the energy at around 7.65 million electron volts. Nobody had ever seen such a state. There was no reason from nuclear theory to expect one. He predicted it purely from the observation that carbon is here. He went to the Kellogg Radiation Laboratory at Caltech and pushed the experimental group, led by Willie Fowler, to look for it. Fowler thought it was a waste of beam time. Hoyle was persistent to the point of being a nuisance. They ran the experiment. It was there, within a fraction of a percent of where he said it would be. That state is now called the Hoyle state, and it is one of the very few predictions in physics made on the grounds that we would not exist otherwise. It also means that essentially, every carbon atom in your body, in the trees outside, in every living thing that has ever existed, got made through a resonance that Fred Hoyle worked out on paper before anybody had detected it. And in 1957, Hoyle, Fowler, and the married team of Margaret and Jeffrey Burbidge published the paper that maps out how stars build the entire rest of the table, element by element, through their lives and their deaths. It is universally known by the initials of its 4 authors. It is one of the most cited papers in astrophysics. The result was that the field arrived at the correct split. The light elements, hydrogen and helium and a little lithium, came from the first 20 minutes. Everything else, all the carbon and oxygen and iron and gold, came later, from stars. Hoyle had proved the second half of the Big Bang's own account of chemistry while trying to demolish it. Fowler received the Nobel Prize in 1983 for the work. Hoyle did not, and the omission is widely regarded as one of the clearest injustices in the history of the prize. But the thing that actually ended the argument was not the chemistry. It was a prediction buried in Alpher and Herman's work that nobody paid attention to for 17 years. Here is the prediction. If the early universe was hot enough to fuse nuclei, it was full of radiation. Enormously energetic radiation, packed in tight, bouncing constantly off free electrons, filling every cubic centimeter of everywhere. That radiation did not go anywhere. There is nowhere for it to go. It is still here, in the room, having been stretched along with everything else, its wavelengths pulled out by a factor of about 1,000 as the universe expanded around it, which drops it out of the visible range, past infrared, down into microwaves. Faint, cold, and coming from every direction with no source you could point at. Alpher and Hermann calculated what temperature it should have by now. In 1948, they published a figure of about 5 degrees above absolute zero. The correct answer is 2.7. For a first attempt at a quantity nobody had ever measured, from a theory nobody believed, that is close enough to be remarkable. And nothing happened. Nobody went looking. Alpher and Hermann raised it repeatedly through the 50s and got very little interest. The radio engineering of the day could arguably have found it. And there is a reasonable argument that a measurement made at Bell Labs by Edward Ohm in 1961 contained the signal already, sitting in an unexplained excess of about 3 degrees that he noted and moved on from. A pair of Soviet physicists, Doroshkovich and Novikov, published a paper in 1964 explicitly stating that the Bell Labs horn antenna in New Jersey would be the ideal instrument to look for the relic radiation. Nobody at Bell Labs read the Soviet journal. The detection, when it came, was an accident, and it was an accident that 2 people spent a year trying to get rid of. Arno Penzias and Robert Wilson were radio astronomers at Bell Telephone Laboratories in Holmdel, New Jersey. Penzias had been born in Munich in 1933 and had left Germany as a 6-year-old on a Kindertransport train, his parents following later. Wilson was from Houston, quiet, precise, and had done his doctorate at Caltech. They had inherited a piece of equipment. The Holmdel horn antenna is a strange-looking thing, a great aluminium funnel about 6 meters across, built in 1959 to bounce signals off the Echo balloon satellites. Once communication satellites moved on, the antenna was surplus, and the 2 of them got it for astronomy. It was the most sensitive radio receiver in the world for its wavelength, and they wanted to use it to map faint radio emission from the Milky Way. To do that, they needed to understand every source of noise in the system, so they could subtract it and be left with sky. They pointed it at empty sky and measured the noise. There was more than there should be. It was not much, about 3 degrees above absolute zero of excess signal. But it would not go away, and they could not account for it. And until they could, the science they wanted to do was impossible. So they began eliminating causes. This took them the best part of a year. They checked the receiver electronics. They checked the antenna joints and taped over the aluminium seams in case they were radiating. They pointed it at New York City to measure urban interference, and the city was not the problem. They considered the possibility of leftover radiation from a high-altitude nuclear weapons test conducted in 1962, and worked out that it should have faded by now, and it had. They rotated the antenna to every part of the sky available to them across a full year, which meant the Earth's own motion had them looking in every direction. The noise was identical from all of them. It did not rise or fall with the time of day. It did not follow the plane of the Milky Way, which ruled out our own galaxy. It did not change with the seasons, which ruled out anything in the solar system. Whatever it was, it filled the sky evenly, and that is a genuinely bizarre property for a signal to have. What kind of source has no direction at all? What is there that arrives from everywhere at once? And then there were the pigeons. A pair of them had nested inside the horn. Pigeons roosting in a large, sheltered metal funnel is entirely reasonable behavior on the pigeon's part, and a considerable nuisance on Penzias and Wilson's. The birds had coated the interior with droppings, which Penzias in his written report described as a white dielectric material, which is one of the finest pieces of scientific euphemism on record. They caught the pigeons. They sent them by company mail to a Bell Labs site some distance away and released them. The pigeons came back, because homing pigeons do that, which the two physicists had apparently not fully thought through. The birds were eventually dealt with by a colleague in a manner Penzias later said he regretted. They climbed into the horn and cleaned it out thoroughly. The noise did not change, at which point they were out of options and quietly miserable about it. They had a beautiful instrument, a signal they could not explain, and a year gone. About 60 kilometers away at Princeton, Robert Dicke had independently worked out that a hot early universe would leave relic radiation, apparently without knowing about Alpher and Hermann's earlier calculation. And he had two younger colleagues, David Wilkinson and Peter Roll, building a small antenna on the roof of the physics building to go and look for it. Jim Peebles had done the theory and had given a talk about it. A chain of conversations got the two groups connected. Penzias phoned Dicke to ask whether he had any idea what the noise might be. Dicke listened, asked a few questions, put the phone down, turned to the room and told his group that they had been scooped. The two teams met, compared notes, and agreed to publish simultaneously in the same issue of the Astrophysical Journal in 1965. Penzias and Wilson's paper is about 600 words long, titled with careful understatement as a measurement of excess antenna temperature. It makes no cosmological claims at all. It simply reports the number and points, in a footnote, at the companion paper by Dicke, Peebles, Roll, and Wilkinson, which explains what it means. That excess antenna temperature is the cosmic microwave background. It is the oldest light in existence, and it ended the argument. Steady state had no explanation for it. Hoyle tried for the rest of his life, proposing thermalized starlight scattered by iron whiskers in intergalactic space, and it never worked, and the spectrum eventually ruled it out conclusively. He went to his death in 2001 unconvinced, having also picked fights over the origin of life, the age of the Archaeopteryx fossil, and several other matters. He was wrong about a great deal, and he was wrong at a level almost nobody ever reaches at all. Penzias and Wilson received the Nobel Prize in 1978. Ralph Alpher and Robert Hermann, who had predicted the radiation, calculated its temperature and spent 17 years trying to get anybody to look for it, were not included. Alpher was reportedly quite bitter about it, and it is hard to argue he had no cause. He received the National Medal of Science in 2005, at 84, and died the following year. So now let's take the thing itself, because the cosmic microwave background is misunderstood in a very specific way, and it is worth clearing up. It is not a picture of the Big Bang. It is not light from the beginning. It is light from 380,000 years afterward. And understanding why it comes from that particular moment tells you almost everything about what the early universe was actually like. Come back to the hot, dense state. Everywhere is filled with a plasma. That means the temperature is high enough that electrons cannot stay attached to nuclei. They are all loose, moving freely, and the protons and helium nuclei are loose too. Free electrons are very good at getting in the way of light. A photon traveling through that plasma goes an extremely short distance before it hits an electron and bounces off in some other direction. Then it hits another one. It cannot travel. It is trapped, scattering constantly, going nowhere on average. That makes the early universe opaque. Not dark, blindingly bright, and completely opaque in the way that the inside of a thick fog is bright and you still cannot see anything through it. Or the way the surface of the sun is, which is exactly the same physics. Now expand and cool for 380,000 years. At some point, the temperature falls to about 3,000 degrees. which is roughly the surface temperature of a cool red star. And below that, something changes suddenly. Electrons slow down enough that when they meet a proton, they stick. Neutral hydrogen forms everywhere in a relatively short span of time. The name for this in the literature is recombination, which is a poor name because the electrons and protons had never been combined before. It is a historical accident from laboratory plasma physics, and it has stuck. And the moment the electrons get bound into atoms, they stop scattering light. The fog lifts. In a geological instant, the universe goes from completely opaque to completely transparent, and all that trapped radiation is suddenly free to travel in a straight line. It has been traveling ever since. 13.8 billion years, in whatever direction it happened to be pointing when it was released. That is the cosmic microwave background. It is the flash of the moment the universe became clear, and it is arriving at your house continuously, from every direction, all the time. The reason it comes from every direction is worth sitting with. It is not coming from a shell of material somewhere far away. It was released everywhere at once, including from the place you are lying. The light released here, left here, long ago, and is now 13 billion light years away, being received by somebody else's antenna if there is one. What arrives here tonight is the light released 13 billion light years away, which has taken all this time to cross. So every day, the light reaching us comes from slightly further out. The surface of last scattering, as it is called, is not a wall. It is the set of places whose release light is arriving right now, and it recedes as time passes. Tomorrow you receive light from a shell, one light day further away. It is a horizon, and like all horizons, it moves when you do. It was 30,000 degrees when it started out. It arrives here at 2.7 degrees above absolute zero. That factor of about 1100 is the amount the universe has expanded since, and it is one of the cleanest measurements in the subject. And for about 30 years, everybody who owned an old television set was picking up a small fraction of it. On an analog set tuned between channels, the static on the screen was mostly terrestrial interference and thermal noise in the electronics. But a small percentage of it, usually put at around 1%, was that radiation. Somewhere under 1/100th of the snow on the screen was the release flash of the early universe, arriving in a living room and being ignored. There is one more thing that light does, and it is a small, strange gift that nobody was expecting. When you measure the background carefully, it is not quite the same temperature in every direction. There is a very slight pattern, hotter in one half of the sky and cooler in the other, at the level of about 1 part in 1,000. That is far larger than the tiny variations we will come to in a moment. And it has a completely different cause. So are we moving, or is everything else? It is us. We are moving. If you travel through a bath of radiation that fills all of space, the light ahead of you gets slightly blue shifted, and the light behind you gets slightly red shifted, exactly as the pitch of a siren changes. So the pattern is a direct readout of our own motion with respect to the radiation, and you can solve for the speed and the direction. The answer is that the solar system is traveling at about 370 kilometers per second toward a point in the constellation of Leo. That is the sum of everything. The Earth around the Sun around the galaxy toward Andromeda, the local group toward the Virgo cluster and toward the great attractor beyond it, all added up into one number. And that is a slightly awkward result, philosophically, because relativity is built on the idea that there is no such thing as absolute rest. There is no preferred frame. No experiment can tell you whether you are moving or standing still. Only how you are moving relative to something else. That principle is the foundation of the whole structure, and it has never failed a test. The background radiation does not break it, but it does provide something quite close to a natural frame of reference for the universe as a whole, because it fills everything evenly and it was released everywhere at once. There is a state of motion in which the background looks the same in all directions, and you can meaningfully call that being at rest with respect to the universe, and we are not in it. We are doing 370 kilometers per second relative to it, in the direction of Leo. And there is nothing we could do about that, even if we wanted to. So the oldest light in existence turns out to double as a speedometer. It was not designed to be one. It is simply what happens when you are moving through something that is everywhere. And that measurement is precise enough that it has to be subtracted out before you can see anything else in the maps. The motion signal is 100 times larger than the actual cosmological variations underneath it. Every published image of the microwave background you have ever seen has had our own velocity removed from it first, along with the glow of our own galaxy across the middle. And what is left after both subtractions is the thing worth looking at. Now, that radiation turned out to have a property that broke the theory almost as soon as it was measured properly, and fixing it required an idea stranger than anything so far. The background is smooth, extraordinarily smooth. Measure its temperature in one direction, and then in the opposite direction. And the two numbers agree to about 1 part in 100,000. That sounds like good news. It is what a uniform early universe ought to look like. But think about what it requires. Take a patch of sky on your left and a patch of sky on your right. The light from each has been traveling toward you for 13.8 billion years. Those two patches are separated by something like 90 billion light years now, and even accounting for the expansion, they have never been in contact. Light emitted from one at the beginning of time has not had the time to reach the other. Not now, and not ever. They have no common history. Nothing has ever passed between them. No signal, no heat, no influence of any kind. So why are they the same temperature to 5 decimal places? Two objects reach the same temperature by exchanging heat until they settle. Put a hot spoon in cold water and wait, and they equalize, and that requires contact. These patches have never had contact. Their temperatures should be independent, and they should differ. That is the horizon problem, and it is severe. The universe appears to have been coordinated across distances that coordination cannot cross. And there was a second problem sitting beside it. Remember Friedmann's family of solutions. Some universes have enough matter to eventually halt and collapse. Some have too little and expand forever. And one sits exactly on the dividing line, geometrically flat, expanding at precisely the escape rate. Measurements say ours is flat, not roughly flat. Flat to within about 0.5% of the critical density, as best as we can currently measure. The difficulty is that flatness is unstable. If the early universe was even slightly off the critical value, the deviation grows. It compounds relentlessly. To be as close to flat as we are today, after 13.8 billion years of compounding, the density in the first second must have been tuned to something like 1 part in 10 to the 15th. Push back to the earliest moments physics can describe, and the required precision becomes absurd. Dozens of decimal places of exactness with no reason for any of them. That is the flatness problem. It is not a contradiction. The universe is allowed to have started that way. But a theory that requires a number to arrive perfectly tuned by luck, with no mechanism, is a theory with a hole in it. The answer came to a young American physicist in December of 1979. He wrote it in his notebook, drew a double box around it, and labeled it a spectacular realization, which is not how anybody normally annotates their own work. Alan Guth was 32 at Stanford on a postdoctoral position, and his career was not going well. He had been on short-term contracts for 9 years. He was working on magnetic monopoles, which are a prediction of certain particle physics theories, and which nobody has ever found. And the question was, why the universe is not full of them. And what he realized was this. Suppose that for an extremely brief period in the very early universe, the expansion was not steady, but explosive. Not the gentle stretching we see now. Exponential growth, doubling and doubling and doubling, on a timescale so short it is difficult to write down. The numbers are almost meaningless as quantities, so hold them loosely. Starting somewhere around 10 to the minus 36 seconds after the beginning, and ending by around 10 to the minus 32 seconds, the universe doubled in size perhaps 60 or 80 times over. That takes a region far smaller than a proton and inflates it to something larger than a grapefruit. And in the process, everything within it gets stretched by a factor that runs to 26 or more zeros. Guth called it inflation. And look at what it fixes. The horizon problem dissolves immediately. Before inflation, the entire region that would become our observable universe was tiny, small enough that every part of it was in easy contact with every other part. Heat flowed, temperatures equalized, everything settled to the same value, in the ordinary way, with no mystery about it. Then inflation took that thoroughly mixed little patch and blew it up enormously, carrying the uniformity outward with it. Regions that appear to have no common history do have one. They were neighbors once, before they were separated by something faster than any signal. The flatness problem goes the same way. Take any curved surface and expand it enormously, and the piece you can see becomes flat. Stand on a beach ball, and it curves away sharply beneath you. Stand on the Earth, and the horizon looks level. Inflate the Earth to the size of the galaxy, and any local patch is flat past the ability of any instrument to measure. The universe does not need to have been born flat. It needs only to have been stretched until the curvature was pushed out beyond where we can see. And the monopoles, which is what Guth was actually working on, get diluted to essentially zero density, which is why nobody has found one. One mechanism, 3 problems, and it was not designed to solve 2 of them. Guth's original version had a flaw. He knew it and said so in the paper. His inflation was driven by the universe getting stuck in an unstable state and then decaying out of it in bubbles, and the bubbles would never merge properly, leaving a chaotic mess rather than the smooth universe we live in. He published anyway, with the problem stated plainly, which is a more honest way to do science than is entirely common. The repair came from Andrei Linde in Moscow in 1981, and independently from Andreas Albrecht and Paul Steinhardt in the United States. Instead of bubbles, the inflating field rolls slowly down a gentle slope in its energy landscape, inflating as it goes, and comes to rest smoothly at the bottom, dumping its energy into ordinary matter and radiation everywhere at once. That energy release is what actually produces the hot, dense state that we call the Big Bang. In the inflationary picture, inflation comes first, and the hot, dense universe is what inflation left behind when it ended. Now I should be straight with you about the status of this, because inflation gets presented with more confidence than it has earned. The evidence for it is real, but indirect. Inflation predicts that quantum fluctuations, tiny random ripples in the field, would have been stretched to enormous size, along with everything else, seeding slight variations in density across the sky. It predicts the statistical pattern of those variations quite specifically, and when the satellites measured the temperature variations in the microwave background, the pattern matched. That is a genuine success, and it is not a small one. But there is no direct detection. There is no consensus on what the field driving inflation actually was, and there are hundreds of proposed versions. And the flexibility of the framework worries a number of serious physicists who argue that a theory able to accommodate almost any outcome is not being properly tested. Paul Steinhardt, who helped build it, became one of its sharper critics for exactly that reason. There is a genuine argument in the field about this, and anybody who tells you inflation is settled is overselling. The predicted smoking gun would be a specific twisting pattern in the polarization of the microwave background, left by gravitational waves from the inflationary epoch. In 2014, a team announced they had found it, and there was a great deal of excitement. And then it was determined within the year that the signal was dust in our own galaxy. That was handled well and quickly by everyone involved, and the search continues. And inflation raises the question that produces more confusion than almost anything else in this subject. So let's deal with it directly. Nothing can travel faster than light. Everybody knows that. So how can space expand faster than light? The answer is that the speed limit is a local rule, and it has always only been a local rule. And this is not a loophole invented to rescue cosmology. What relativity forbids is anything moving through space past you faster than light does. If two objects pass each other, their relative speed cannot exceed light speed. That restriction is airtight and has never been violated in any experiment. It says nothing at all about how fast the distance between two distant points can grow when the growth is caused by the expansion of the space between them. Nothing is moving through anything in that case. No object is being accelerated. No signal is outrunning a light beam. The galaxies are sitting still in their own neighborhoods, and the road between them is getting longer. Think about the elastic strip again. If the elastic stretches at a fixed rate per centimeter, then a bead far enough away recedes as fast as you like, simply because there is more elastic between you and it. Double the distance, and you double the recession rate, with no upper limit anywhere in the arrangement. No bead ever slides along the elastic. Every bead stays glued exactly where it was. There is a specific distance where the recession rate reaches light speed. It is called the Hubble radius, and it sits around 14.5 billion light-years out. Beyond it, galaxies recede faster than light, and there are a great many of them, and it is entirely ordinary, which leads to a number that sounds like an error and is not. The universe is 13.8 billion years old. The observable universe has a radius of about 46 billion light-years. That looks impossible. Light has only had 13.8 billion years to travel, so how can anything be 46 billion light-years away and still be visible? Because the space in between kept growing while the light was in transit. A photon that set out toward us shortly after the beginning has covered 13.8 billion years of travel time. Yes. But the ground it crossed early on has been stretching ever since it passed. The galaxy that emitted it has been carried outward the whole time. It is not where it was. It is now about 46 billion light-years away. And the light arriving from it tonight left a place that no longer exists at that distance. So the observable universe is a sphere about 93 billion light-years across, containing perhaps 2 trillion galaxies, and every one of them is further away now than the light we are receiving from it suggests. And here is the part of that which is quietly sad, and which I think about more than is entirely reasonable. Because of dark energy, the expansion is accelerating. The Hubble radius is not staying still relative to the galaxies. Distant galaxies are slipping across it, one by one, out of the region from which anything can ever reach us again. Once a galaxy crosses that line, no light it emits after that moment will ever arrive here. Not because it has been destroyed, and not because it is moving away too quickly in the ordinary sense, but because the road between us is lengthening faster than light can travel it. We will keep seeing those galaxies. Their old light is already in transit, and will keep arriving, increasingly redshifted, increasingly faint, frozen ever closer to the last instant before they crossed. But nothing new from them will come. They are, in the only sense that matters, gone. The observable universe is emptying, slowly and by our standards at an unimaginably leisurely pace, but it is emptying. In 100 billion years, an astronomer in what is left of this galaxy will look out and find a sky containing our own merged local group, and nothing else at all, with no way to discover that the rest was ever there. We happen to be alive during the period when the evidence is still visible. That is not a comforting thought or an uncomfortable one, particularly. It is just where we are in the sequence. There is a question that follows naturally from all of that, and it is one of the better ones, so let's take it before we go further. If space is expanding everywhere, is it expanding here, in this room, between the atoms in your hand? And the answer is that it is not. And the reason why is one of the more satisfying details in the whole subject. Expansion is not a force. It does not push on things. It is a description of how the overall geometry of the universe behaves when it is averaged out over enormous distances and treated as smooth. And the universe is only smooth at enormous distances. On any smaller scale, it is extremely lumpy. And where it is lumpy, gravity has already won. Take the solar system. The sun holds the planets in orbit through a local gravitational arrangement that has been stable for 4.5 billion years. That arrangement is not in any competition with the expansion, because the expansion is not a wind blowing outward. There is nothing to resist. The orbit is set by the local geometry, which is dominated overwhelmingly by the sun's mass, and the large-scale behavior of the universe simply does not enter into it in any measurable way. The same goes for the galaxy, which is held together by its own mass and its dark matter halo. The same goes for the local group, which is bound, which is why Andromeda is approaching us rather than receding. The same goes for a cluster of galaxies, and that is roughly where the boundary sits. Structures bound by gravity do not expand. The gaps between unbound structures do, and well below that, the other forces take over entirely. The Earth holds itself together electromagnetically and gravitationally. Your body is held together by chemical bonds, which are electromagnetic, and those are stupendously stronger than any conceivable cosmological effect at that scale. An atom is held together by the electromagnetic attraction between the nucleus and the electrons, and a nucleus by the strong force. And those are stronger still by margins that are difficult to overstate. So you are not being stretched. The room is not getting bigger. Your bed is exactly as long as it was this morning. The expansion is happening in the enormous quiet gaps between galaxy clusters, where there is nothing bound and nothing to hold, and those gaps are getting wider, and everything else is carrying on as it was. There is a version of the raisin bread analogy that captures this well. As the dough rises, the raisins move apart. But the raisins themselves do not swell. They are held together by being raisins, and the dough expands around them. Now I should flag something here, because there is a genuine argument among cosmologists about how literally to take the phrase space expands. And it is not the kind of argument that makes headlines, but it is real. The picture we have been using, where space is a kind of medium that stretches and carries galaxies along with it, is the standard teaching picture, and it is enormously useful. It gets the answers right. But a number of serious people, including John Peacock and others, have argued that it can be misleading, because the split between expanding space and galaxies sitting still in it depends on a choice of coordinates rather than being a physical fact. In relativity, you can describe the same situation in different coordinate systems, and there are perfectly good ones in which nothing is expanding, and the galaxies are simply moving apart, and the redshift comes out identical either way. Which of those is the real description is arguably not a physics question at all. The measurable things, the redshifts, the distances, the temperature of the background, the arrival times of light, are the same in every description. The stretching rubber is a picture we hang on the mathematics to make it thinkable. And it is a good picture, and it is not the mathematics. I mention it because you will occasionally run into somebody insisting that space does not really expand, and they are not a crank. And they are also not saying that the universe is static. They are saying something more subtle about coordinates, and both accounts predict the same sky. Here is the thing worth keeping from all of that. The expansion is not an event happening to objects. It is a statement about the changing relationship between distant things that are not bound to each other. It has no effect on anything you can touch. It is not a pressure, and it will not do anything to you tonight. There is one more version of this confusion that is worth clearing, because it comes up constantly, and the answer is short. People ask whether the Big Bang is still happening. And in a real sense, the answer is yes. The expansion that began then has never stopped. It slowed for the first several billion years as gravity pulled back against it. And then, around 5 or 6 billion years ago, it began speeding up again as dark energy came to dominate, and it is continuing tonight. There was no moment when the Big Bang ended and something else began. The event and the aftermath are the same process, and we are inside it. What did end was the hot part. The fireball cooled out of existence within the first 400,000 years, and the universe has been transparent and cooling ever since. But the expansion that defines the whole picture is ongoing, and every measurement of a distant galaxy's redshift is a direct observation of it happening now. And a related one. People ask whether the Big Bang could happen again, somewhere else, and whether we would see it. Within the standard picture, no. There is no mechanism for a new hot dense state to appear inside an existing cold universe. Within eternal inflation, other regions are still inflating and still ending their inflation and producing their own fireballs continually. But they are outside our horizon by construction, and always will be, receding faster than any signal could cross. So there is nothing to see, and no possibility of there ever being anything to see, which is either a limitation or a mercy, depending on how you feel about the idea of a new universe starting up in the neighborhood. So let's walk the sequence itself. From the earliest moment, physics can say anything about forward, slowly, and with the honest labels attached, because the confidence level drops sharply the further back you go, and it is worth knowing which parts are measured and which parts are sketched. Start at the beginning of the description, which is not the same as the beginning of the universe. There is a duration called the Planck time. it is about 10 to the minus 43 seconds. That is a decimal point, followed by 42 zeros, and then a 1 in seconds. And there is no comparison that makes it meaningful, so do not try to feel it. Below that scale, the two great theories of physics contradict each other. General relativity describes gravity as smooth, continuous geometry. Quantum mechanics describes everything else as discrete, probabilistic, and fundamentally uncertain. At ordinary scales, they never meet, because gravity is negligible for particles and quantum effects are negligible for planets. In the first Planck time, the entire universe was small enough and dense enough that both apply at once. And when you make them apply at once, they produce nonsense. Infinities. Answers that are not answers. So the honest statement is that we have no theory of that interval, not an incomplete theory. None. Anything you have heard about what happened in the first 10 to the minus 43 seconds is speculation dressed in mathematics, and the people doing the speculating will generally tell you so. After that, the ground firms up slightly, and it is still very soft. Somewhere in the region of 10 to the minus 36 seconds, the strong nuclear force is thought to separate out from the others. The picture here is that at sufficiently high energies, the fundamental forces are aspects of a single interaction. And as the universe cools, they crystallize apart, one at a time, the way water at a certain temperature stops being one thing and becomes ice with a definite structure. This is called symmetry breaking. It is well motivated. It has never been tested at the relevant energies and cannot be by an enormous margin. Inflation, if it happened, happens around here. A patch of space smaller than a proton, stretched in an unmeasurably brief interval into something the size of a grapefruit or a beach ball. And then, the inflating field decays and dumps all of its energy into a flood of particles and radiation. That moment, technically called reheating, is the point at which the universe becomes the hot, dense fireball that the phrase Big Bang describes. By 10 to the minus 12 seconds, we are in territory that particle accelerators can reach. The Large Hadron Collider at CERN, on the border between Switzerland and France, smashes protons together at energies comparable to the universe at around this age. So from here forward, we are not guessing. We are working with physics that has been measured in a laboratory. At this stage, the universe is a plasma of quarks and gluons. Quarks are the constituents of protons and neutrons. And in the world you live in, they are permanently confined, never found alone, always bound in groups. At these temperatures, they are not. They move freely in a soup, and that soup has been recreated briefly in heavy ion collisions, and it behaves, surprisingly, like a liquid with almost no viscosity at all. Around a millionth of a second in, the universe has cooled enough that the quarks can no longer stay loose. They bind in threes, and protons and neutrons come into existence for the first time. And here is where something happened that nobody can fully explain. And it is the reason there is anything to talk about. In that early plasma, matter and antimatter were produced together. Every process that creates a particle creates its antiparticle alongside it. And every time a particle meets its antiparticle, they annihilate and turn entirely into radiation. That is not a theory. That is measured behavior every day in laboratories. If the early universe had contained exactly equal amounts, then the annihilation would have been total. Every particle would have found a partner. The result would be a universe containing nothing but photons, expanding and cooling forever, with no matter in it at all. No stars, no planets, no chemistry, nothing. That did not happen because there was a slight imbalance. For roughly every billion antiparticles, there were about 1,000,000,001 particles. Everything annihilated. The overwhelming majority of the matter in the early universe was destroyed, and it went into the radiation bath. And that radiation is the background you are being rained on tonight. There are roughly 1,000,000,000 photons in the microwave background for every proton in existence, which is precisely the ratio you would expect from that accounting. And the 1 part in 1,000,000,000 that had no partner is everything. It is every galaxy, every star, every rock, the chair in the corner of your room, and you. You are made of the leftovers, the surplus that survived because the books did not quite balance. So why was there a surplus? Why 1 part in 1,000,000,000 rather than a clean 0? Why they did not balance is called the baryon asymmetry problem, and it is unsolved. There are conditions known to be necessary for it, laid out by the Soviet physicist and dissident Andrei Sakharov in 1967. And there are processes in the Standard Model that violate the relevant symmetries slightly. But the amount of violation we can measure falls short of what is needed by an enormous factor. Something else was going on, and nobody knows what. It is one of the most important open questions in physics, and it does not get anything like the attention that dark matter and dark energy do. 1 second in. The universe is about 10 billion degrees. Neutrinos, which barely interact with anything, stop interacting altogether and go their own way. They are still traveling now, a cosmic neutrino background from 1 second after the beginning, older than the microwave background by a very long way, and far too weak to detect with any technology that currently exists. Detecting it would be one of the great experiments of the century, and there is no obvious route to it. At about 10 seconds, the last of the electron and positron pairs annihilate. Between roughly 2 minutes and 20 minutes, nucleosynthesis runs, the window we talked about. Protons and neutrons fuse into deuterium, then helium, and the process runs into the missing rungs at mass 5 and mass 8 and stops. Out comes about 75% hydrogen and 25% helium by mass, with a trace of deuterium and a whisper of lithium. And then everything is too thin and too cool for fusion to continue. That composition is testable, and it is one of the strongest confirmations we have. The deuterium abundance in particular is a superb measurement, because deuterium is fragile and stars destroy it rather than making it, so any deuterium found anywhere is primordial. The measured amount pins down the density of ordinary matter in the early universe to a few percent, and then nothing much happens for 380,000 years. That is a long stretch of a bright opaque fog, slowly thinning, slowly cooling, the same everywhere, with sound waves rolling through it. Actual sound waves, pressure oscillations in the plasma, because a hot, dense medium supports them exactly as air does. The wavelengths were enormous and the frequencies far below anything an ear could register, but they were real acoustic waves, and their fingerprints are the single most useful measurement in modern cosmology, which we will come back to. Then, recombination. The fog lifts. The background radiation is released. And now comes the strangest chapter, which almost never gets mentioned. After the fog lifted, the universe went dark. The released radiation redshifted out of the visible range fairly quickly, and there were no stars. None. Nothing was burning anywhere. There was hydrogen and helium gas, cooling, drifting, very slightly clumpy, and no light source at all in the whole of existence. That period is called the Cosmic Dark Ages, and it lasted somewhere between 100 million and 250 million years. A universe already vast, entirely transparent, entirely empty of light, filled with cold gas quietly falling toward the places where it was already slightly thicker. Which brings up a fair question. If the early universe was smooth to 1 part in 100,000, how did anything ever clump at all? A perfectly smooth gas stays smooth. The answer is that it was not perfectly smooth, and the tiny variations were enough. And gravity does the rest by an inherently unfair process. A region very slightly denser than average pulls slightly harder. It gathers a little more material. Now it is denser still, so it pulls harder still. The rich get richer, without limit, and a whisper of an imbalance in the early gas becomes a galaxy given enough time. Except that ordinary matter alone cannot do it fast enough. Run the calculation with only the atoms we can see, and the structures do not form by the time we observe them. The radiation pressure in the early universe keeps normal matter smoothed out, resisting collapse, until quite late. Dark matter is what fixes that. Whatever it is, it does not interact with light at all, so it was never held up by the radiation pressure. It began collapsing earlier, building a scaffolding of dense regions across the universe, while ordinary matter was still being kept smooth. When the fog lifted and the gas was finally free, it fell into structures that were already waiting for it. So the first stars formed in dark matter halos that had been assembling for 100 million years or more. And those stars were nothing like the ones outside your window. Made of pure hydrogen and helium, with no heavier elements at all, they could not cool efficiently while collapsing, which meant they formed enormous. Hundreds of times the mass of the sun, blazing blue-white, burning through their fuel in a couple of million years and dying as violent supernovae. Nobody has ever seen one. They are the great prize of current infrared astronomy. And the James Webb Space Telescope has been pushing into that era and finding galaxies earlier and brighter than the models comfortably predicted, which is currently generating a good deal of productive argument. Those first stars lit the universe again, and their radiation stripped the electrons back off the hydrogen gas between the galaxies, which is called reionization. And it finished somewhere around 1 billion years in. And then galaxies assembled, and merged, and made more stars, and enriched the gas with the heavier elements from their deaths. And after 9 billion years or so of that, in an ordinary spiral galaxy, an ordinary star formed in a cloud that had been enriched by generations of earlier deaths, and around it, a disk of leftover debris condensed into planets. You are made of the ash of that process. The hydrogen in the water in your body is primordial, made in the first 20 minutes and essentially unchanged since. Everything else in you was assembled in stars that finished burning before the sun existed. Which leaves the one question that everybody asks eventually, and that I have been putting off. What was there before the Big Bang? The short answer is that nobody knows. The longer answer is more interesting, because it explains why the question might not have an answer at all, and also why it might. And there is no way at present to tell which. Start with the singularity, because that word does a great deal of unearned work in popular accounts. When you run the Friedmann equations backward, the scale factor of the universe shrinks toward 0. And as it does, the density and temperature climb toward infinity. At the mathematical limit, you get a state of infinite density in 0 volume. That is the singularity, and it is often described as though it were a tiny hot object that existed for an instant before exploding. It was not an object. It is not a description of anything. It is a place where the theory stops producing meaningful output. Infinity is not a physical quantity. You cannot measure it, you cannot build with it. And when it appears in the middle of a calculation about the real world, it is almost always a signal that the equations are being used outside the range where they apply. That has happened repeatedly in physics. The equations of classical electromagnetism give an infinite energy for a point charge. The classical description of a hot object gives infinite energy at short wavelengths, which was the crisis that produced quantum mechanics in the first place. In every case, the infinity was not a discovery about nature. It was the theory announcing its own limit. General relativity is a theory of smooth, continuous geometry. It contains nothing quantum. As the universe shrinks toward the Planck scale, quantum effects on the geometry itself become dominant, and general relativity has no way to represent them, so it keeps producing numbers, and the numbers stop meaning anything, and eventually they run away to infinity. Roger Penrose and Stephen Hawking proved a set of theorems in the 1960s showing that under quite general conditions, singularities are unavoidable in general relativity. Given a universe like ours, running it backward within the theory produces one, and no reasonable adjustment avoids it. Those theorems are correct and important, but what they actually establish is that general relativity predicts its own failure, which is a somewhat different and much more useful statement than the universe began at a point. So the honest position is this: the Big Bang Theory does not describe the beginning of the universe. It describes what happened after a certain very early moment, and it does that superbly, with measurements agreeing to several decimal places. What happened at or before that moment requires a theory of quantum gravity, and there is not one. There are candidates. There is no accepted answer, no experimental test, and no obvious prospect of one soon. Within that gap, several serious proposals live, and it is worth walking a few of them, with the caveat that none is established, and some may not be testable even in principle. The first is that the question is malformed. This is Hawking's position, and it is the most disorienting of the lot. Time is not a backdrop in general relativity. It is part of the geometry, woven together with space, and it is affected by matter and energy the same way space is. So if the geometry itself is what breaks down at the beginning, then time breaks down with it. Asking what happened before is asking about a moment that has no existence, using a word that has no referent there. Hawking's image for this, which he used often, was to imagine walking north on the Earth. You keep going north. You reach the North Pole, and then you ask, what is north of that? The question is fine as English. There is simply no such direction. You have not hit a wall, or a boundary, or an edge. The North Pole is a perfectly ordinary place, with nothing special about it locally, and the coordinate system just runs out there because of how it is built. In Hawking and Jim Hartley's no-boundary proposal, time near the beginning behaves less and less like time and more like another dimension of space, smoothly, with no sharp edge anywhere. And the universe is finite in the past, without having a first moment. It does not begin. It just does not extend indefinitely backward. That is either profound or a sleight of hand, depending on who you ask. And it is mathematically respectable, and it is entirely untested. The second family of proposals says there was a before, and it was another universe, or this one. Bounce models take the collapse seriously and then have it stop. Instead of shrinking to a point, the universe contracts to a very small but finite size. Quantum effects on the geometry generate an enormous repulsion, and it rebounds outward. What we call the Big Bang was the bounce. There was a previous phase, contracting, possibly for a very long time, and it turned around. Loop quantum cosmology, which comes out of one particular approach to quantising gravity, produces exactly this behavior in its simplified models. Space is discrete in that framework, made of finite chunks, and you cannot compress it past a certain point because there is nothing smaller to compress into. Some cyclic models chain these together indefinitely, a universe that expands, collapses, and rebounds forever. Paul Steinhardt and Neil Turok have developed versions of this in some detail, partly as a deliberate alternative to inflation. The third family says our Big Bang was one event among many, and it is the one most physicists would bet on if forced. And it is also the least satisfying. If inflation happened, it turns out to be hard to switch off everywhere. The field driving it decays in some regions and keeps inflating in others. And the inflating regions expand so fast that they always outrun the decaying ones. So inflation ends locally and continues globally, forever, spawning pocket universes endlessly. Each one is a region where inflation stopped, heated up, and became a hot, dense fireball that its inhabitants would call a beginning. This is called eternal inflation, and it emerges rather naturally from the equations rather than being put in by hand, which is what makes it hard to dismiss. In that picture, our Big Bang is a local event. It is the moment inflation ended in our patch, not the start of everything. And the greater structure has been going on for an unbounded time and will continue without limit. Whether that constitutes a theory or a story is genuinely argued about, because the other pockets are causally disconnected from ours by construction, and no observation can reach them. A number of extremely capable people consider this a serious problem. A number of equally capable people consider it an unavoidable consequence of equations we have good reason to trust. That argument is live, and it is not close to resolution. And there is a fourth answer, which is the most common one among working cosmologists in private. And it is that they do not know, and it does not currently matter for their work. That is not evasion. Nearly everything measurable happens after the first tiny fraction of a second, and the theory covering that period is in excellent shape and is tested constantly. The beginning itself is a boundary condition that current physics cannot reach, and pretending otherwise would be a worse offense than admitting it. So if you take one thing from this section, take this. The Big Bang theory is not a theory of the origin of the universe. It is a theory of the history of the universe, from a very early moment to now, and it is extremely well supported. The origin remains open. Those are two different claims, and merging them is where most of the public confusion about this subject comes from. There is one more piece of confusion worth clearing before we start heading back down, and it is about what the theory is competing against. People sometimes say the Big Bang is just a theory, meaning a guess. In ordinary speech, a theory is a hunch. In science, a theory is a framework that has survived attempts to kill it and that makes predictions specific enough to be wrong. So what did this one predict before anybody measured it? And could those predictions have failed? It predicted that distant galaxies would recede in proportion to distance. That was confirmed by Hubble and Humason and has been extended to enormous distances since. It predicted a specific primordial chemistry, roughly 3/4 hydrogen and 1/4 helium, plus trace deuterium and lithium. Measured, and it matches, including in gas that has never been near a star. It predicted a relic radiation bath at a few degrees above absolute zero, filling the sky evenly with a very particular spectral shape. Measured, accidentally, by two men trying to remove it from their data. It predicted that the temperature of that radiation was higher in the past. This one is lovely, and hardly anyone mentions it. You can measure the temperature of the background radiation at earlier epochs by looking at how it excites molecules in distant gas clouds. And those clouds are seen as they were billions of years ago. The measured temperatures come out higher by exactly the amount predicted by the expansion. A thermometer reading from 10 billion years ago, and it agrees. It predicted that distant galaxies would look different from nearby ones because we see them younger. They do. The early universe is full of small, irregular, furiously star-forming galaxies, and the orderly spirals come later. Any one of those could have come out wrong. The helium fraction could have been 2%. The background could have been absent, or lumpy, or at 40 degrees, or with the wrong spectrum. The distant gas clouds could have shown the same temperature as today, which would have been fatal. None of them failed. And the steady-state theory, which was a real competitor with capable people behind it, was killed by exactly this process. It made predictions. The predictions were wrong. Its advocates fought hard and lost on the evidence, which is how it is supposed to go. And the fact that it lost is a point in favor of the whole enterprise rather than against it. Which brings us to what we can actually measure now, and to the 2 or 3 places where the numbers currently refuse to agree. For 25 years after Penzias and Wilson, the microwave background was known to be smooth, and that was almost all anybody could say about it. Ground-based instruments could not do better, because the atmosphere above them glows in microwaves and drowns out the detail. You had to get above the air. And in November of 1989, after 15 years of development and a redesign forced by the loss of the Space Shuttle Challenger, NASA launched a satellite called COBE, the Cosmic Background Explorer, into a polar orbit. It carried 2 instruments that mattered. One measured the spectrum of the background with great precision. The other looked for variations in temperature across the sky. The spectrum result was presented at a meeting of the American Astronomical Society in January of 1990 by John Mather, and the data had been taken over 9 minutes of observation. He put up a plot showing the measured points against the theoretical curve for a perfect thermal emitter at 2.73 degrees above absolute zero. The points sat on the curve. All of them. The error bars were smaller than the thickness of the line used to draw the curve, so the plot appears to show a smooth theoretical prediction with no data on it at all. The room stood up and applauded, which is not something that happens at astronomy meetings. It is the most precise thermal spectrum ever measured, from anything, anywhere, and it is the signature of radiation that was in complete equilibrium with hot matter. Nothing else makes a curve like that. Every alternative explanation for the background, including Hoyle's iron whiskers, died in that plot. The second result took 2 more years of data, and it is the one people remember. George Smoot announced in April of 1992 that COBE had found the temperature variations. They are minute, about 1 part in 100,000, which is to say that if you took the map of the sky and expressed the hottest and coldest spots as a fraction of the average, you would need 5 decimal places to see the difference. But they are there, they are real, and they are the seeds. Those are the density variations that gravity spent 13 billion years amplifying into every galaxy in the sky, including this one. Smoot described looking at the map as being like looking at God, in a comment to a journalist that he seems to have regretted almost immediately, and that followed him for years. Mather and Smoot shared the Nobel Prize in 2006. COBE's resolution was poor by later standards, about 7 degrees, which is 14 times the width of the full moon. It could see that there were variations. It could not see their structure. WMAP followed in 2001, parked at a gravitationally convenient point about 1.5 million kilometers out from Earth on the far side from the Sun, where it could keep the Sun, Earth, and Moon all behind it and stare into the dark. It mapped the sky at about 1/3 of a degree, which was a leap of more than 20 times, and the Planck satellite, launched by the European Space Agency in 2009 to the same location, did better still, mapping the whole sky in 9 frequency bands at 5 arc minutes, with detectors cooled to 1/10 of a degree above absolute zero, which made them for a while the coldest known objects in space. What those maps contain is the reason cosmology stopped being an argument and became a measurement. Remember, the sound waves rolling through the plasma before recombination. Here is what they were doing. A slightly denser region pulls matter in with gravity. As matter piles in, the radiation pressure builds and pushes back out. In, out, in, out. An oscillation with a well-understood physics running for 380,000 years. Then the fog lifts, the radiation escapes, and the pattern freezes exactly where it was at that instant. Some regions were caught at maximum compression, which makes them slightly hotter. Some at maximum rarefaction, slightly cooler. Some in between. So the pattern of hot and cold patches on the sky is a photograph of a standing wave, and the sizes of the patches tell you the wavelengths that were oscillating. And the relative strengths of those wavelengths tell you what the medium was made of. You can extract that as a plot of variation strength against patch size, and it comes out as a series of peaks, and those peaks are the acoustic peaks, and they are the single richest dataset in cosmology. The position of the first peak tells you the geometry of space, because it fixes a known physical size at a known distance, and comparing angle to size measures the curvature the light crossed. It says flat to within about 0.25%. The height of the second peak relative to the first tells you how much ordinary matter there is, because ordinary matter feels the radiation pressure and its inertia damps alternate peaks. The third peak tells you about the dark matter, which does not feel radiation pressure at all and so affects the pattern differently. And out of that, plus supernova measurements and the distribution of galaxies, comes the standard model of cosmology, which is the current best account, and which is not a hunch. The universe is 13.797 billion years old, give or take about 20 million. It is flat to the limits of measurement, and its contents are strange. About 5% of it is ordinary matter, meaning atoms, meaning everything anybody has ever touched or seen or built an instrument out of. About 27% is dark matter, which has mass and gravity and does not interact with light and has never been identified. And about 68% is dark energy, which is the name for whatever is causing the expansion to accelerate, and which is not understood at all. That last one arrived in 1998 from 2 competing teams measuring distant supernovae in order to find out how fast the expansion was slowing down. Both teams found it was speeding up. Neither believed their own result at first, and both spent months hunting for the error. And the fact that 2 rival groups got the same unwelcome answer independently is most of why it was accepted. Saul Perlmutter, Brian Schmidt, and Adam Rees shared the Nobel in 2011. The mathematical form dark energy takes in the equations is a constant energy density in empty space that pushes outward, which is the cosmological constant. the same term Einstein put in to hold the universe still, and then removed once expansion was discovered, and which he is supposed to have called his greatest blunder, a phrase we only have second-hand from George Gamow, and which may well be Gamow embellishing. So the term Einstein invented for the wrong reason, and then withdrew, turns out to be in the equations after all, carrying 2/3 of the total contents of the universe, and doing something he never imagined. That is not vindication exactly. It is stranger than vindication, and it comes with the worst quantitative disagreement in the history of physics attached to it. If dark energy is the energy of empty space, then quantum field theory ought to be able to calculate it, because quantum field theory says empty space is not empty and is full of fluctuating fields with a ground state energy. So people calculated it. The answer comes out too large by a factor of about 10 to the 120th power. That is a 1 followed by 120 zeros. It is not a near miss. It is the largest gap between a theoretical prediction and a measurement that has ever been recorded in any field. And it has been sitting there, unresolved, for decades. Everybody knows about it. Nobody has fixed it. So we have measured the composition of the universe to a few percent, and we cannot say what 95% of it is. Both of those statements are true at once, and living with both of them is roughly what the current state of the field feels like from the inside. And there are cracks, not fatal ones, as far as anyone can tell, but real, and it would be dishonest to end without them. The largest is called the Hubble tension, and it is about a number we have already met, the rate of expansion. There are two ways to measure it, and they are independent, and they both work, and they disagree. The first way is the direct one, and it is a modern version of exactly what Hubble and Humason did. Build a ladder. Use parallax, the apparent shift of nearby stars against the background as the Earth moves around the Sun, to get direct geometric distances to the closest ones. Use those to calibrate Cepheid variables, using Leavitt's relation. Use Cepheids in nearby galaxies to calibrate a particular kind of supernova, which always detonates at very close to the same brightness and is visible across enormous distances. Then use those supernovae to reach far out into the expanding universe. That ladder gives a rate of about 73 kilometers per second per megaparsec. The team led by Adam Rees has been refining it for years. And the James Webb Space Telescope has now checked the Cepheid photometry independently and largely confirmed it. The second way never touches a ladder. You take the microwave background, which encodes the physical size of those sound waves at recombination, feed it into the standard model, and calculate what the expansion rate must be today for everything to be consistent. That gives about 67.4. Those two numbers are not compatible. The gap is around 8%, and the error bars on both have been shrinking for 20 years. And the disagreement has got worse rather than better as the precision improved. The statistical significance is now above 5 standard deviations, which in particle physics is the threshold at which you announce a discovery. For a long time, everybody assumed somebody had made a mistake in the calibration, and enormous effort has gone into hunting for it, and nobody has found it. Independent methods have been brought in. Red giant stars used as a distance indicator give an answer in between, closer to 69 or 70, which muddies rather than settles things. Gravitational lensing time delays give numbers on the high side. Gravitational wave events used as standard sirens are promising and not yet precise enough. So which of them is wrong? Or is neither of them wrong, and the model sitting between them is missing a piece? So there are two possibilities. Either there is a subtle systematic error in one of the two methods that a great many capable people have failed to find, or the standard model of cosmology is missing something between recombination and today. Nobody knows which. It is the most active argument in the field, and it may turn out to be the crack that lets the next theory in, or it may turn out to be a calibration problem in a photometric 0 point. And the honest answer today is that it is undecided. The second crack is smaller and older, and it involves lithium. Big Bang nucleosynthesis predicts hydrogen and helium beautifully. It also predicts a small amount of lithium-7. And when you measure lithium in the atmospheres of the oldest, most metal-poor stars in our galaxy, the ones assumed to preserve primordial material, you find about 1/3 of the predicted amount. Not a rounding error. A factor of 3, consistently, across many stars, in a measurement that has been repeated for 40 years. The likeliest explanation is that it is a stellar problem rather than a cosmological one, and that lithium in those old stars gets circulated down into the interior over billions of years and destroyed, because lithium is fragile and burns at a relatively low temperature. There are models for that, and they roughly work. But no one has closed the case, and there are people who take it as a hint of new physics in the first few minutes. It is a small, persistent discrepancy that refuses to resolve. There are also some odd features in the microwave background maps themselves. There is a region in the southern sky, usually called the cold spot, which is larger and cooler than the statistics comfortably allow. There are hints of alignments between the largest scale patterns that should be randomly oriented and do not appear to be. The individual significances are modest, and with a whole sky to look at, you will always find some feature that seems unlikely. And the community is properly cautious about reading meaning into them. Planck confirmed that the anomalies WMAP saw are in the data and not instrumental, which raised the interest level somewhat, and there it sits. And there is the sharpest new one, which is only a couple of years old. A survey called DESI, running on a telescope at Kitt Peak in Arizona, has been mapping the positions of tens of millions of galaxies to measure how the expansion rate has changed over time. Its early results contain a hint, and it is currently no more than a hint, that dark energy may not be constant after all, that its strength may have been slightly greater in the past and be weakening now. If that holds up, it is not a small correction. A cosmological constant is constant by definition. Something that changes over time is a different animal entirely, a field of some kind evolving through the history of the universe, and it would rewrite a substantial part of the standard model and change the predicted long-term fate. It might not hold up. Early hints frequently do not. More data is coming, and the significance may well shrink back into the noise, and quite a few cosmologists expect it to. But it is currently the most interesting number in the field, and it is worth knowing that the 95% of the universe nobody understands may be about to get more complicated rather than less. So that is the honest state of it. The overall picture is secure and tested from about a second onward. The composition is measured precisely and interpreted poorly. The expansion rate has 2 respectable values that will not reconcile, and the beginning itself remains outside the reach of any theory anybody has. That is a more comfortable place to be than it sounds. A subject with no loose ends is a subject that is stopped. So let's come back down now, slowly, and gather the confusions up one more time. You do not need to follow closely. Most of this you have already heard tonight, and hearing it again in a quieter form is the point. The first confusion is the name. The Big Bang was not a bang, and it was not big. It was not an explosion in space. It was an expansion of space, everywhere, all at once, from a state that was hot and dense in every location, rather than in one location. The name came from a radio broadcast in 1949 from a man who was arguing against the idea, and it stuck because it sounded good, and 13,000 people have since failed to improve on it. The second confusion is where it happened. It happened here, in the space your bed occupies, and in the space above your roof, and in the space between the Earth and the Moon, and at every point in the observable universe simultaneously. There is no location you could travel to and find the site. Every location is the site. The third is what it expanded into. Nothing. There is no outside. The expansion is a change in the internal geometry measured by rulers that live inside, and general relativity has no term for an exterior because the mathematics it is written in describes curvature from within. North of the North Pole is a grammatical sentence that points at nothing. The fourth is whether we are at the center. We are not, and neither is anybody else, because there is no center. Every observer, everywhere, sees the same recession, rising with distance, and every one of them has an equally good claim, which means none of them has one. The fifth is the redshift. Distant galaxies are not fleeing through space. They are sitting in their own neighborhoods, and the road between us is lengthening, and light stretches as it crosses stretching ground. A redshift is not a speed. It is a record of how much bigger everything has become since that light set out. The sixth is the speed limit. Nothing moves through space faster than light, and this has never been violated. The distance between 2 points can grow faster than light without anything moving at all, because that growth is not motion, which is why the observable universe is 46 billion light-years in radius after only 13.8 billion years, and why there are galaxies we can see whose light will never reach us again. The seventh is the microwave background. It is not a picture of the Big Bang. It is the flash from the moment the universe stopped being opaque, 380,000 years in, when electrons finally settled onto nuclei and the fog lifted. It was 3,000 degrees when it was released, and it is 2.7 degrees now. And the difference between those numbers is the amount everything has stretched since. And the eighth is what came before, and the answer is that nobody knows, and that the theory called the Big Bang was never a theory about the beginning in the first place. It is a theory about the history. It works from about a second onward and is tested to several decimal places, and the first instant is a boundary where the equations announce their own failure and hand the problem to a theory of quantum gravity that does not exist yet. That is the whole set. Every one of them comes from taking a word that means something inside the universe and applying it to the universe as a whole, where it stops meaning anything. Explosion, center, outside, before. Perfectly good words, each one of them useless at that scale, and the confusion was never yours. It was built into the language. And the people. It is worth holding them for a moment, because this is not a story about equations. It is a story about a long relay of people who mostly did not know what they were carrying. Poe, dying in Baltimore, having worked out that the dark sky means the universe has an age, in a book nobody read. Leavitt, going deaf, at 30 cents an hour, finding the relationship that would let everybody else measure the sky, and being moved on to other work before she could use it herself. Friedmann, the meteorologist who flew bombing missions and balloon flights, deriving the expanding universe 7 years early, publicly told he was wrong by Einstein, vindicated, and then dead of typhoid at 37, 4 years before Hubble proved him right. Lemaitre, the priest in Leuven, deriving it again independently, publishing it in a journal nobody read, being told his physics was abominable, and then cutting his own priority claim out of the English translation because he genuinely did not care who got the credit. Slipher in Arizona, holding a plate open for 30 hours at a time to catch the light of a galaxy and handing over the numbers. Humason, the mule driver who left school at 14 and became one of the finest observers of the century. Hubble, who was difficult and vain and did the work, and who never quite believed what the work meant. Gamow, who tried to escape the Soviet Union in a kayak with chocolate and brandy, and who worked out what a hot beginning would have cooked. Alpher and Hermann, who predicted the background radiation and its temperature and spent 17 years asking somebody to look, and who were not on the Nobel citation. Hoyle, who spent his life trying to demolish the theory, coined its name by accident, and along the way worked out how carbon is made in stars, because he was made of carbon, and therefore it had to be possible. Penzias and Wilson, who spent a year trying to eliminate the oldest light in the universe from their data, and who cleaned pigeon droppings out of a horn antenna in New Jersey before accepting that the noise was real. Guth, on a short contract, out of options, writing a spectacular realization in a notebook in December. Mather and Smoot and the COBE team putting up a plot where the data was hidden under the thickness of the theoretical line and getting a standing ovation for it. None of them saw the whole thing. Each of them got one piece, usually while trying to do something else, often while convinced that the piece they were holding meant the opposite of what it meant. That is what the process actually looks like from inside. Not a march, a relay run in the dark by people passing objects to each other without knowing what they are. So let's come down through it, from the outside in, and take our time about it. Start at the edge of what can be seen. 46 billion light-years out in every direction, a sphere about 93 billion light-years across. And the boundary is not a wall or a shell or a surface. It is just the distance beyond which light has not had time to arrive. Past it, almost certainly, the universe continues, possibly without end. There is no reason to think the far side of the horizon looks any different from here, and no way to check. Come in. Inside that sphere there are perhaps 2 trillion galaxies, and they are not scattered randomly. They are arranged along filaments, sheets, and knots, with enormous near-empty voids between them, in a pattern that people call the cosmic web, because it genuinely does look like one. That pattern is the direct descendant of the temperature variations in the microwave background, amplified by gravity for 13 billion years. And the shape of it can be predicted from those variations with fairly good accuracy, which is one of the more remarkable achievements of computational physics. Come in further. Our galaxy sits on the edge of a supercluster, and beyond it is a cluster in Virgo. And past that, the whole local flow of galaxies is drifting toward a concentration of mass called the Great Attractor, which sits inconveniently behind the plane of our own galaxy, where the dust makes it hard to see. Come in again. The local group. Around 80 galaxies, mostly small, dominated by 2 large spirals, the Milky Way and Andromeda, with the Triangulum galaxy a distant third. Andromeda is one of the very few galaxies in the sky that is blue-shifted rather than red-shifted, because it is bound to us gravitationally and is falling inward at about 110 kilometers per second. In something like 4 billion years, the two will begin to merge, and the merger will take a further couple of billion years to settle. And almost no stars will collide during it, because the distances between stars are so large compared to the stars themselves. The two galaxies will pass through each other largely untouched, and then fall back together. And the sun, if it is still burning, will simply be carried along. Come in again. The Milky Way, a barred spiral, 100,000 light years across, perhaps 200 billion stars, with a black hole of 4 million solar masses at the center that we have now photographed. The sun sits about 26,000 light years out, in a minor arm, and takes something like 230 million years to complete one orbit. The last time it was in this position, the dinosaurs had not appeared yet. Come in again. The solar system. 1 star, 8 planets, a belt of rubble, a scattering of moons, and a vast cold cloud of comets extending perhaps a light year out. The whole thing condensed 4.5 billion years ago from a cloud of gas and dust that had been enriched by the deaths of earlier stars, which is where every heavy atom in it came from. Come in again. The Earth, a rocky planet with liquid water on the surface and an atmosphere with free oxygen in it, which is unusual and is a product of life rather than a precondition for it. Come in again, wherever you happen to be, a building, a room, a bed, weight on a mattress, air moving in and out, the particular quiet of a house at night, and come all the way in. You are made of atoms, and every one of them has a history that runs the entire length of what we have just walked through. The hydrogen in you is primordial. It has not changed since the first 20 minutes. Every hydrogen nucleus in every water molecule in your body is a single proton that formed when the universe was about 1/1,000,000th of a second old and has been intact ever since, through everything. It was in the plasma. It was in the fog. It drifted through the dark ages. It fell into a cloud, and into a star, and out again, and eventually into a river, and into a glass, and into you. It is 13.8 billion years old, and it is currently part of you, and it will be part of something else afterward. The carbon in you was made inside a star, through a resonance that Fred Hoyle predicted on the grounds that he existed. The oxygen you are breathing came out of stars too. The iron in your blood was forged in the last moments of stellar collapse, or in the collision of 2 neutron stars. And either way, it was made under conditions violent enough that nothing about them is survivable. And it is now sitting quietly in you doing the ordinary work of carrying oxygen around. And the light is still arriving. Right now, tonight, in the room you are in, about 400 photons per cubic centimeter of the cosmic microwave background, passing through the walls, through the blankets, through you, at a rate of many trillions per second across the surface of your skin. Cold light at 2.7 degrees that was released 380,000 years after the beginning and has been traveling in a straight line ever since. And its journey ends here, in the dark, on you. You are not observing this from outside. There is no outside. You are made of the material. You are being rained on by the evidence. And the expansion we spent 3 hours discussing is happening in the room, in the gaps between the galaxies you cannot see, quietly, at a rate of about 70 kilometers per second for every megaparsec, which over the width of a bedroom amounts to nothing at all, and over the width of the visible universe amounts to everything. And it keeps going after this, which is worth a moment before we stop. The sun has about 5 billion years of ordinary burning left, and then it will swell into a red giant. and the inner solar system will not survive that in any recognizable form. But the galaxy will carry on making stars for a long time after, and so will every other galaxy. And star formation across the universe is already past its peak, but has an enormous slow tail ahead of it. In 100 billion years, the accelerating expansion will have carried everything outside the merged remains of our local group past the horizon, and the sky will contain one galaxy and nothing else. And there will be no way for anybody living then to discover that the rest was ever there. The evidence will simply have left. In 100 trillion years, the last of the small red stars will finally run out. They burn slowly, which is why they last. And when the smallest of them go dark, there will be no new light being made anywhere. After that, it is a long, quiet business of drift and decay. Cold remnants orbiting each other, occasionally colliding, occasionally being flung out of what is left of the galaxies. Black holes growing slowly, and then, over spans of time that make everything so far look instantaneous, evaporating away by the slow leak that Stephen Hawking worked out in 1974. And then, something very close to nothing, spread very thin, at a temperature approaching, but never quite reaching absolute zero, expanding forever. That sounds bleak written down, and it does not particularly feel bleak, and I think the reason is the timescales. None of it is scheduled to interfere with anything. The numbers involved are so far past anything that has meaning that they stop functioning as a warning and start functioning as scenery. We are living, as it happens, in the brief, noisy interval near the start when there are stars, and the sky is full of things to see. The whole history of everything that has ever mattered to anybody fits inside that interval with room to spare. And there is no evidence that being early makes it worth less. So, let that settle for a moment. Somewhere around 13.8 billion years ago, for reasons that remain outside the reach of any theory anybody has built, everything that exists was in a state of enormous density and temperature, everywhere at once, with no outside and no elsewhere. And then it expanded, not into anything. It simply became larger and cooler and less crowded, and it has been doing that ever since without stopping. In the first minutes it made hydrogen and helium. For 380,000 years, it was a bright, opaque fog. Then it cleared and released a flash of light that is still crossing the room you are lying in. It was dark for 100 million years or more. Then gravity, working patiently on variations of 1 part in 100,000, gathered the gas into the first stars, and those stars made the heavier elements and died and scattered them, and the next generation did it again, and again, for 9 billion years, until an ordinary star formed in an ordinary arm of an ordinary galaxy, with a disk of enriched debris around it that became planets, and on one of them, a while later, some of that material arranged itself into a form that could look up and wonder why the night sky was dark, and take 300 years to work out that the answer was that the universe has an age. That is the whole story. That is everything we have. Notice how much of it is unfinished. The beginning is unreachable. 95% of the contents are unidentified. The expansion rate has 2 respectable measurements that will not agree with each other. The reason there is matter at all rather than nothing is not understood. These are not small gaps, and nobody is hiding them. And none of that is a problem you need to hold tonight. Your body is doing the only part that concerns you. Air in, air out. The heart running its own timing. Hydrogen from the first 20 minutes moving through you in every drop of water. Carbon from the inside of a dead star holding the shape of your hands together. The oldest light in existence arriving continuously on your skin at a temperature just above absolute zero, having crossed everything, ending here, You do not have to remember any of it. Not the names, not the dates, not the numbers, not Friedmann or Lemaitre or Leavitt, not the horn antenna in New Jersey, not the difference between recombination and reionization. None of it was ever a test. If you retained one image out of 3 hours, the elastic with the beads on it, or the exclamation mark after the word VAR, that is more than enough. And if you retained nothing, that is fine too. The universe is not waiting on your attention. It expanded for 13.8 billion years before there was anybody to notice. And it will keep expanding long after, at the same quiet rate, into no place, from no center. It does not need to be understood in order to continue. It does not need anything from you at all. The galaxies are drifting apart tonight, the way they have every night. The background radiation is arriving the way it always has. The hydrogen in the water in your body is as old as the first minute and is not in any hurry. So let all of it go now. There is nothing to hold. The light has been traveling for 13.8 billion years to reach this room, and it is here, and it is very cold, and it is very faint, and it is landing on you in the dark. Rest.